Dear colleagues, I would like to wish you a good morning. It's unfortunately only a wish because currently Kyiv is under air alert. So we probably have some delays, but there are many people who were able to join online. Several people are present in our offline venue at Francevich Institute for Problems of Material Science. So we should probably try to keep the schedule at least a little bit as it goes, and we have an intent to go on with the schedule as it is. So today's first symposium during the day is Advanced Ceramics and Glasses. We have several excellent talks from our distinguished researchers during this session. We have also several talks dedicated to new research from younger researchers, and I hope that it will be possible to uphold the good traditions that Ukrainian, but also international material science community hold in the area of producing advanced ceramics, of researching advanced ceramics, of moving on with new interesting ways to change, to influence the field that is already, I would say, really established. Perhaps one of the oldest fields in material science. And with that brief introduction, I would like to announce our first speaker for today. It's a keynote speech from an excellent, distinguished researcher, Ukrainian researcher in the field of ceramic materials and composite materials, Professor Tetiana Prikhna from Bakul Institute for Super Hard Materials of National Academy of Science of Ukraine. Professor Prikhna is also member of Ukrainian Academy of Science, academician of Ukrainian Academy of Science, and also member of several other international academies and research societies. She's our constant supporter, and for that we are really grateful. I mean, as a conference, as a HighMatTech conference, and always when she speaks, she gives a very in-depth, very interesting speeches, and I think today's will not be an exception. And the speech Professor Prikhna is going to present is titled Hot Pressed and Manufactured Under High Pressure, Ultra High Temperature Hafnium Boride and hafnium diboride and hafnium diboride silicon carbide ceramics. Professor Prikhna, please, if you could share your screen.
Mm-hmm. Do you see my presentation?
We now see the window, but could you put it into full screen if possible?
I will put in full screen, but I'm not sure that it will be how to say,
I think you could try. You could try.
is it now okay?
No. Could you press that button? Yeah.
Yes, I know, but I think I opened presentation, which in PDF format. Sorry, I will open PPT format.
It should work too. The PDF format should work too.
What about such?
So
Now you see? Because if I'm in PPT format, sometimes I can't change slides. Now you see my slide?
We see the slides, but we see also the interface of the program. So perhaps.
But I will shift it. I can't shift it more.
Maybe pressing F11, you can change it in full screen mode.
The second button from the right in your program, try pressing it. Two arrows, one pointing up and one down. The second from.
I tried, but I think it's not working. And do you see that I changed slide or not? Do you see changing slide or not?
No. We now see the application window. So probably maybe stop sharing and try sharing the screen again.
Okay. Sorry, I will open PPT presentation better. I think I opened not correct presentation in PDF format because sometimes I can't change slides if I am in full PPT mode. Wait a moment, I will. Wait a moment. Sorry, excuse me, please. I can't find my presentation. Wait a moment.
Yeah. We have some time.
Sorry. I try to do this. And is it better now? No?
It's the PDF again. It's the PDF again.
Sorry.
No.
I can try to show PPT. Also, I opened, but sorry. This is PDF, PPT, or?
Yeah, it's PDF again. Professor Prichner, maybe you could send the PDF to us, and we will.
I sent already both PPT and PDF to you at night today.
Yeah. Just a second.
I'm really sorry that we didn't launch it from here. Please wait a moment, and we will do it from here.
So wait.
So just a minute, and I think.
Okay, thank you.
Is it visible for now clearly?
Yes, I see.
Yeah, but
just a second. Yeah. full mode screen.
Mhm.
And do you see changes the slides?
Now
Or
I
not?
see no, I don't see now slides at all.
The second one or
Oh,
at all?
It's
we
first
have it.
one, just now
We
first
have it.
one. And second one, can you show me second one for any
We,
case?
we now see them. Professor Krishna,
Okay.
can you see the slides?
Yes,
too?
I see. I see.
Okay, so please.
You hear me well? Yes, all is okay?
Yeah, everything is great.
Okay.
Let's start.
So, good morning, ladies and gentlemen. I'm very happy to make my presentation at such conference. I'm very grateful for such introduction, and I'm also very grateful to all people who protect our country from enemy and make possible to make this presentation at this nice conference. So this work was performed in cooperation between several research institutes of Ukraine, is Institute for Superhard Materials, Institute for Problems of Material Sciences, Institute for Semiconductor Physics, and also University, Kyiv Polytechnical University. Besides, we cooperate with Polish Radom University and also with University of Department of Institute of Chemistry from Slovakia Academy of Sciences. I have big list of collaborations, maybe not all even mentioned, but I put the key authors. Please push next slide. Can you change slide, please?
I have changed, but
thank you.
just a second.
Thank you. Yeah, I see you now. The outline of my talk will be as following. First of all, I will tell about motivation, possible applications, and best results presented in literature connected with these materials. Then I will explain method of preparation. We will use high pressure technique. It's 4 gigapascal pressure and 1,800 degrees centigrade at the highest what we can reach using our equipment, and also hot pressing materials prepared under 20-30 megapascal. I will explain about mechanical characteristic of hafnium diboride, and I will compare them with mechanical characteristics and properties of zirconium and tantalum diboride based ceramics. We study structure by X-ray, scan electron microscopy, transmission electron microscopy, and Auger spectroscopy. Then we also study melting temperature in vacuum by Piranha Arthenium technique. It was made in Francevich Institute for problems of material sciences, but we made it only for high pressure sinceride material. And also I will explain results of differential thermal analysis and thermogravimetrical study in air up to temperature 1600 degrees centigrade of our ceramics. Then I will explain ablation tests, which up to temperature 2780 degrees centigrade in air. It was made in Slovakia Academy of Sciences. And then the last section, I will explain about effect of amount of silicon carbide addition and its physical and chemical characteristics of this addition on mechanical properties and stability against ablation of hafnium diboride silicon carbide composites. And then I will make conclusions. Please change slide. So it is well known that ultra-high temperature transition metal borides, for example, such as hafnium diboride, zirconium diboride, tantalum diboride, can be used in a wide range of applications, for example, as components of military and commercial equipment operating in extreme conditions, in rockets engine, hypersonic aircrafts, and re-entry vehicles, as protective coating for graphite, and for example, for manufacturing even of cutting tools. This application requires the development of materials with significantly improved physical properties, capable of operating in both neutral and oxidizing and aggressive environments at temperatures up to 1,600, 2,000 degrees centigrade, and even above. An analysis of the literature shows that the additions of silicon carbide, zirconium carbide, niobium carbide, titanium diboride, tantalum diboride, zirconium silicide, molybdenum silicide, silicon nitride leads to an improvement in the mechanical properties and corrosion resistance of ceramics based on hafnium diboride, zirconium diboride, and tantalum diboride. So the aim of this study, we think that using ultra high pressure, 4.1 gigapascal, high temperature, 1,800 degrees centigrade, it's so-called technique HiPHT. It's such abbreviation will be during my presentation, and also hot pressing under pressure up to 30 megapascals, temperature 1,750 to 2,000 degrees centigrade. Hot P, it will be abbreviation for this technique. And due to we will make purposeful formation of solid solutions with mentioned additives, we expected to attain further improvement of mechanical characteristics and stability against ablation. In fact, from practical point of view, we would like to use this material to prepare nozzles, which you can see in the right low corner, for a gas turbine engine. And we want to find the most suitable material from all mentioned above. Please, next slide. So here you can see the data from literature. What we found, the best data for tantalum diboride, hafnium diboride, zirconium diboride. We tried to use the so-called optimal amount of additions and temperatures, try to both synthesize material under hot pressing and high pressure conditions. Please, next slide. And for this, we use equipment, hot press equipment, HiPHT. There are press 5 kilonewton efforts or press 140 kilonewton efforts for bigger size samples and for samples up to 63 millimeter in diameter. In principle, we can apply pressure up to 7.7 gigapascals. But in this study, as I told, we used 4.1 gigapascal pressure and temperature 1,800 degrees centigrade. So temperature was limited because of tools what we use in the present study. Also, we have hot press system shown in the middle of this slide. And all this high pressure equipment and hot pressed equipment located on the territory of our institute in Kiev. And also we cooperate with Radom University in Poland, which have spa plasma sintering. Currently, Professor Edwin Heverkian from Kharkiv is working in this institute, and he helped us with making experiments under spa plasma sintering conditions. Thank you. Please, next slide. So we used commercially available powders. But before we investigated X-ray, we X-ray examined these materials, make grid field refinement to look for additions which can be present or impurities which can be present in these materials, estimated lattice parameters. And also when we prepared our composite materials, we mixing them or in mill for 24 hours, or we use high-speed planetary activator and metal balls, and we mixed only for 3 minutes. Next slide, please. So for estimate characteristics, we used the usual traditional equipment for micro hardness testing or hardness testing, fracture toughness testing. We have this Falcon 500 hardness tester with load on indentation load from 200 grams to 63.5 kilograms. Then we also use transmission microscopy. This microscope located in Germany. We also cooperate in German Institute of Material Science and Physics in Dresden. And also we use scanning Auger microscopy. In principle, this microscope combines both methods, all methods of scanning electron microscopy and also Auger spectroscopy. Auger spectroscopy more sensitive for light elements and allow us to study quantity, to make quantitative analysis of very small inclusions up to 2010 nanometers in diameter. And then also we used ultrasonic examination and traditional tests for estimated, for example, compression strength or bending strength. Please, next slide. Here I would like to show you results of our study of pure tantalum diboride, zirconium diboride, and hafnium diboride sinterid materials under hot pressure. It is first results. Then under high pressure, high temperature, you see we estimated micro hardness under 1 kilogram load and under 5 kilogram load. Here presents the results and also fracture toughness of these materials. And then high pressure hot press materials. And for spa plasma sintering, we just started these investigations and we just studied samples based on tantalum diboride. And here we present our results of tantalum diboride. And for zirconium diboride and hafnium diboride, we present the best results found in literature. So you see that in principle, hardness and fracture toughness are rather high, but not so. And we found that we can really improve these characteristics by different additions. Next slide, please. So here I show you just to show you which additions we used and which composition we tried to sinterate. But I must tell that the best characteristics we obtained when we add silicon carbide additions in amount of 20-30 weight percents, both for all zirconium diboride, tantalum diboride, hafnium diboride, and all methods what we used. This addition occurred the best from point of view of improvement of mechanical and characteristics and test on ablation, for example. Next, please. So here you can see hot pressed results of hot pressed material, tantalum diboride with silicon carbide for for comparison. But I must tell that hardness and fracture toughness by silicon carbide with this material, we did increase. We slightly increased Young modulus. And next, please, next slide. Also, in case of high pressure, high temperature treatment at 4.1 gigapascal, we got some high hardness, very high hardness, high fracture toughness for material with tantalum diboride with silicon carbide, but we didn't succeed to densify at all. We got only powder after such treatment of pure tantalum diboride. Despite in literature, we meet such results that can be consolidated at 1,200 degrees centigrade. In our experiments, we didn't succeed. But for silicon carbide addition, we also got very high critical current density. And this study is still in progress because we have only mechanical properties for such compositions. Next, please. So this is the results of study of also tantalum diboride-based material by spa plasma sintering, and we observed comparatively high hardness, the last row, and fracture toughness very high for these materials. But I must tell that materials with silicon carbide additions are very difficult to analyze, I mean, the fracture toughness, because it's very difficult to see because of big contracts between different phases where crack is finished. We try to do our best, but I must tell that I'm not very rely on fracture toughness tests from absolute values. I mean, we can compare, of course, we try our best, as I told. Next, please. So here you can see structure obtained by scanning electron microscopy in two modes. First line is composition mode, where you can see the phase composition of the material. The more bright phase, it's more heavy phase. And downline, you can see secondary electron images of the materials, pure tantalum diboride with 38% of silicon carbide, tantalum diboride with 20% of molybdenum disilicide, in tantalum diboride with 30% of zirconium disilicide. And the best from point of view of density is tantalum diboride with 30% of silicon carbide. This material was prepared under hot pressing conditions, and this material, the most dense, demonstrated the highest characteristics. And also I must tell that we practically have the same amount of silicon carbide after sintering as we had before as a powder. In case of, for example, molybdenum disilicide or zirconium disilicide, we have much less in sintered material phase of these additions. It means that we have intensive interaction and formation of solid solution. While I must tell that also some solid solution formed even with silicon carbide additions as well. Please, next slide. Here I show you X-ray study and result, and the down we have result of composition of Rietveld refinement of different phases. And in principle, I tell about this that for silicon carbide addition, this is high pressure, high temperature prepared materials. So we didn't reduce amount of powder which we added after sintering, practically no reduction. Next, please. Here you can see the study of ADX analysis of this material, but prepared under 4 gigapascal pressure. We're told in principle we don't see interaction by X-ray, notable interaction. We didn't very exactly analyze the variation of, for example, lattice parameters. I mean, on formation of solid solutions. But here you see down, if you look on the results, we see that we really have a small amount of solutions of tantalum, boron, silicon, carbon, oxygen, or tantalum, silicon, carbon, oxygen in the matrix material, in bright matrix, especially in this light gray, a little bit more dark areas of this sample. Next, please. So here I would like to show you results of comparison study of zirconium diboride and hafnium diboride based material prepared under hot pressing technique. It is X-ray data which show that silicon carbide addition in principle in the same amount before and after adding this sample, after sintering. Next, please. There are properties of the, this is also characteristics of high pressure, high temperature influence of on structure of this material. Next, please, I will later make conclusion. So, and there are mechanical characteristics of materials prepared under 4 gigapascal and under hot pressed for zirconium diboride with silicon carbide, and hafnium diboride with silicon carbide. We observed that addition of silicon carbide and applying of 4 gigapascal or 4.1 gigapascal pressure and temperature 1800 degrees centigrade allow us to get material with very high Vickers hardness. There are hardness under different load, 1, 5, and 10 kilograms, and also high fracture toughness. And for zirconium diboride materials, we also have improvement when we used high pressure conditions, but not to such extent, and as we used it for hafnium diboride. So in our opinion, hafnium diboride material is have more higher mechanical properties than zirconium diboride based material. Downstairs, down on this slide, you can see literature data. The best what we found for spar plasma sintering material, we found only results of Vickers hardness study. And you see that our results are slightly better than this found in literature. Next, please. Here, we would like to compare also zirconium diboride and hafnium diboride based materials prepared by different methods, hot pressing, HPHT is under high pressure, and also spar plasma sintering. We compared from right side, you can see micro hardness, and from another side, it is fracture toughness of these materials. And in both cases, we observed that hafnium diboride with 30% of silicon carbide additions had the highest absolute values of hardness and fracture toughness. Next, please. So here we compare the mechanical characteristic on single phase and composite materials obtained by high pressure, high temperature technique and by hot pressing. Is there are another mechanical characteristics such as Young modulus and also logarithmic decrement, which demonstrate the dampenability of the material, results of compression strength study, and also tensile strength, which made by ultrasonic examination. We load tablet with ratio 1 to 3, I mean diameter in 3 times bigger than height of this. We put it on the edge and correct and put load on this on the top of disc. And then when it cracked, in principle, we can estimate tensile strength in such a way. We didn't make it with really bars. So you see that properties are rather high. And also we want to mention that we like hafnium diboride material with 38% of silicon carbide. Next, please. As I told you, we want to study beginning of melting temperature in vacuum. It was made in Francevich Institute. And for this, we use this Pirani acerum technique. For this, we produced such sample that you can see on the left. We made special proportions and we drill in the middle hole for 2-3 lengths of this edge. And we put sample in a special chamber with glass window. We can make vacuum, we can make argon atmosphere in this chamber, but then we make heating via this window by laser. Laser should be focused on this hole, which we drilled, and it is very small hole. And then also outside you have a special device to see when the first drops start to form inside this opening. I must tell that at the beginning we made these walls between opening and side walls distance was much bigger, but in this case it was not enough power of laser to heat up our material to start melting. So we must reduce this age. And because of this, some of material before even melting appeared cracks at very high temperatures because of very small age. Next, please. Next slide, please. Here we see results of study of our material based on zirconium diboride and hafnium diboride pure and with silicon carbide additions before heating up to this melting point and after heating. I must tell that pure zirconium diboride and hafnium diboride, we were not able to heat up to melting temperature because their melting temperature usually about 3,200 degrees centigrade, and our materials were already cracked at 2,970 degrees centigrade. But we are sure that at least they are stable up to this temperature, that melting didn't start. With silicon carbide addition essentially reduce beginning of melting of composite, and it's around 2160 degrees centigrade you see everywhere. And what we also observed, but even after this short heating up to high temperature, at room temperature, we measured also hardness and fracture toughness, and we found a lot of reduction of mechanical characteristics of this material. As I repeat, we treat it heated in vacuum. Next, please, slide. I want to show what happened with our structure before and after heating in these conditions. Here you can see mapping of different present components, elements, boron, hafnium, carbon, oxygen, zirconium, aluminum as a mixture. And first, in the red frame, there are you can see photo of this material made in secondary electron mode and composition electron mode. And then you can see the distribution of elements, and we see rather homogeneous distribution of boron and hafnium, some impurity of carbon, maybe it's also in some porous or material, porous after grinding, but homogeneously distributed. This is material prepared under 4 gigapascal pressure, 1,800 degrees centigrade. Next, please. Slide. But after heating to 2,900 degrees, 2,970 degrees centigrade, and even before melting, we observed another picture. You see also in red frame the photos, and in other it is mapping, ADX mapping of distribution of elements, and we very nice observe if we look on boron distribution, the most bright look areas which contain the highest amount of this element on each map. So the boron come to the boundary of grains, and grains caused a lot after such heating. Next, please. So here you can see structure of hafnium diboride with 38% of silicon carbide, also prepared under high pressure conditions. And also first two pictures are photos, and other pictures are distribution of elements. You see hafnium and silicon carbide. And next slide will show you how it's changed structure after. No, next slide will be Auger spectroscopy study. Please, next slide. Here we made also, before I show you a ADX study, it seems that there were no interaction between hafnium diboride and silicon carbide. But when we made Auger mapping, which is more sensitive for light elements, you see that we have formation of solid solutions in these cases. That carbon, for example, diffused to hafnium, and also some silicon diffused, and we found that it's despite on X-ray we don't observe interaction or notable interaction. So Auger spectroscopy studies show us that in principle small amount diffused in this material and interaction occurred. Next, please. And here it is the result of a study of the same material after heating up to 2,000, 1,150 degrees centigrade. You see the slightly changed grains, and also you see the distribution of elements. There are ADX mapping. Next, please. So then we also, as I told, we study stability by thermogravimetric TGA, DTA study of stability in flowing artificial air using CITERAM device. It was made in Germany in EFW EFV Double Institute. We heat with temperature 10 Kelvin per minute. Next, please. And what we made here, you see a comparison of curves, DT8 and TG curves for hafnium diboride and hafnium diboride with 30% of silicon carbide. Upper part is pure hafnium diboride. Why there are two graphs? Because we heat material 2 times. The yellow line show us heating temperature. The blue line is DTA curve and green line is TG curve. The right scale is green scale, and this is green line. It's correspond to results of TG study, thermogravimetric study. And you can see that at first heating, if you follow green line, the oxidation appeared more intensively than after second heating. Then we cool down material and heat second time, as I told. And low row show us the same for silicon carbide. And we also see that silicon carbide provoke more fast oxidation of material. Oxidation starts at lower temperature and go more intensively, because if you see on the scale, it is on the upper scale, it is 3 or 0.8 milligrams, but in lower case, lower row, it is 14 and also higher amount of this react material. But as we will see later, this more fast oxidation maybe is useful because it is prevent material from destruction during ablation test, about which I will tell you later. Next, please. Here we compare pure hafnium diboride with zirconium diboride in air as in TG-DTA study. And we observed that hafnium diboride oxidize much less than pure zirconium diboride. All materials were prepared under high pressure, high temperature conditions, 4.1 gigapascal pressure. Next, please. So this is, we compare the also hafnium diboride with 40% of silicon carbide prepared under high pressure conditions, and also zirconium diboride with 38% of silicon carbide. And we observed also that hafnium diboride less oxidized than zirconium diboride. Next, please. So this is TEM study of our materials after heating to 1600 degrees centigrade in this artificial air. After this TEM-DTA analysis, after 2 times heating, and we still observed a high amount of defects such as twins, dislocations, which also can be the reason, or not only solid solution formation, it can be the reason of increasing of mechanical characteristics of our material. Next, please. The material were FIB cutted. Now I go to the last section, is a study of silicon carbide morphology, composition, structure, and amount on mechanical characteristics and ablation stability of hafnium diboride and hafnium diboride silicon carbide composites. Because we found out that it's very important, all these characteristics and different so-called quality of silicon carbide affect to high extent the properties of hafnium diboride materials, ceramics. Next, please. We use 4 different types of powder. You see from the left side, there are different types of powder with big grains, not sharp grains with sharp edges. And for example, small grains, it is a so-called second and third type. And on the D slide, you see practically round-shaped pseudo-cubic grains. Looks like single crystalline grains of this material. I must tell that first type in the right up and opposite, left type right up and right down. So type 1 and type 4 were the best of this material. We also study approximate composition and admixtures by scanning electron microscopy, by microprobe analysis. And we found out that stoichiometry of silicon carbide of this first and fourth type, you can see down these results in this table, are silicon carbide, silicon carbon 1.5 around. In all materials except the fourth powder, present some admixture oxygen, which can be notable by this ADS study. And I must tell that stoichiometry of silicon carbide on the second and third type, they contain much more high amount of carbon and high amount of oxygen. On the right side, you can see how looks like mixture of hafnium diboride with 38% of silicon carbide. And you see still black unmilled grains, big grains which stay after milling in high-speed planar activator. We mixed with 4 type of powder, which has single crystalline grains in this case. Next, please. So we made ablation test. We didn't, it is next one, yes. Okay, we make ablation test as I told, in Slovakia Academy of Sciences in the Institute of Chemistry. And here you can see this heme. This flame was, distance between flame and sample was 13 millimeters. Sample was near 2 millimeters in thickness and around 15 millimeters in diameter. And this special installation was prepared to analyze, they make by pyrolysis check temperature, put this gas mixture of oxygen and C2H2, and then this is gas burner. Next, please. So here you see results of our study of different samples with different, after this ablation tests. Down you can see graphs. We heat up at, as I told, at 2790 degrees centigrade. And here we keep it up to 150 seconds at these conditions of 100. You see the graph how we increase temperature and reduce temperature. And I must tell that only 3 samples in our case really withstand ablation test. This is, if you look on the pictures on the upper row, this is second sample. Despite you see crack in the middle with 20% additions of silicon carbide of this 4 type, but he withstand. Crack appeared later. We were able to heat up sample up to 2,700, up to 2,000, around 2,700. Down you see on graph temperatures up to which each sample was heated. And other materials, for example, with another with 30% of silicon carbide of second type and third type were cracked at much more lower temperatures. And also withstand the best characteristics was for hafnium diboride with 30% of silicon carbide when we use powder of 4 type and first type. And also we increased the amount of silicon carbide after 40 weight percent, and in this case sample also cracked earlier. So then you see also in the right low corner, you see a nozzle which we prepared from hafnium diboride with silicon carbide of first type. And it is just in wort. It should be to adjust or cutting to make really nozzle from this material. But we stopped on this material with hafnium diboride and with silicon carbide of first type, also because we have such silicon carbide in high amount. And it's not so easy to get single crystalline material. And also I must tell that this material has different structure, the powder. The powder of first type has better structure, better silicon carbide. And other powders are so-called 6-ash structure. Next, please, slide. So what I want to show here, you see the structure of this sample, and we observed that if we use silicon carbide of 6-ash structure, it's more interact with hafnium diboride than beta silicon carbide, because after sintering, we observed less amount of this phase in the densified material. And here you can see the density of this material, porosity, but we estimated it from measurement of sizes and weighed our material. And so this is the best, as I told, we think it is 30% of powder silicon carbide of 4 type or 1 type. Next, please. So, and here you can see also characteristics of this material. And also by stars, we marked near number, we marked samples with which we performed ablation test. And you see the characteristics of these materials. Next, please. We try to find correlation between the mechanical characteristics and stability against ablation of this material. If you look on low graph, the squares, we marked temperature, maximum temperature was where reached for best, so-called Bézier, or some samples which are compatible. And also we observed that for this highest temperature, we simultaneously we found the best the highest Young modulus and hardness of the material. But I must tell that it is not very regular, and we don't see very strict correlation. If you look on the upper graph demonstrates how varied mass loss with increase of amount of silicon carbide in hafnium diboride. You see pure, first dot is pure hafnium diboride, then you see 20%, 30%, and the different silicon carbide, first and fourth type. The mass loss when it was 30% of addition was practically the same. And then if you see 40% of silicon carbide, the last dot on the upper graph, it is the stability or mass loss reduced, but as I told, this sample didn't pass this ablation test, and we want to clear up why it happened. Next, please. So here you can see structure of materials for 4 slides up, prepared from different powders. Silicon carbide, first, second, third, and fourth type. And in case of first and fourth type, it's A and D. We observed that in principle, hafnium diboride formed some frame in this material, while in other samples, we see less contacts between grains of hafnium diboride. The lowest picture show us structure of pure hafnium diboride material. Next, please, slide.
Professor Prichna, we are getting behind the schedule, so
sorry.
if
It's
possible,
last slide.
It's extremely interesting, but
no, sorry. So you can see mapping of silicon and hafnium in different materials with different amount. And what we observed, if we add 30%, so we have frame from silicon carbide, and we think that this is the reason why this material did withstand this ablation test. Next, please. This is this is results what we study how influence initial silicon carbide on structure of hafnium diboride. Next, please. I will tell in conclusions. And this is so when we performed this study, we found, of course, influence of all parameters of silicon carbide, and there are the following. The best composites fabricated from hafnium boride with 2030 silicon carbide, mass loss was 0.25 milligram per second, and we get temperature to 1780 degrees centigrade. And then I observed that the best silicon carbide where stoichiometer silicon carbide carbon was 1.5, about 1.6, and less amount of oxygen in the initial silicon carbide, 0 or 0.1. Then we also observed that hafnium diboride with 30 mass percent different from 40 mass percent addition of silicon carbide, because when we have more silicon carbide, it forms framework which prevent for good mechanical characteristics. Next, please. And this is a coding X-ray study. So better silicon carbide less effect to interact with materials that 6H silicon carbide. Well, in both cases, we formed solid solutions of these materials. So in principle, I finished. I think that all was I told about, and I have more conclusions, but thank you. Excuse me for overpass the limit. Sorry.
I really didn't want to interrupt
No.
you because,
It's okay.
because
Sorry, I was
it's
going
an excellent presentation, very interesting results, and I even hear in the audience that people had questions, but then suddenly they didn't have them because they were answered by the following slide.
Okay, thank you.
But still, on the other hand, I would like to discuss it for several hours if possible.
Thank you. Later, we will make it in private conversation.
But still, although we a little bit behind the schedule, I hope we could discuss several questions. Maybe someone in the audience has something to ask online.
Can I ask question, Matt?
Please.
Yeah, please, Professor Kusilkin.
Professor Prichna. Hello, really
Hello.
excellent presentation.
Oh,
My question is very simple. Did you check mechanical properties after oxidation? Before, yes, but after oxidation, same properties after?
Yes, we checked. I didn't present here. In principle, which from after ablation test, you mean?
Yeah.
We on the surface we checked it is oxidized layer, so of course it's different properties. But from the backside, it was very practically very near, because backside of this 2 millimeter sample practically had the same characteristics like before ablation tests.
Okay, thank you very much.
I will show maybe in next presentation. I will show you the difference result. But we really made this estimation.
Okay, thank you very much. That was the most interesting part for me, because we made a lot of good ceramic, but did not check at first ablation and then the properties after ablation. But that's next story. You are right.
I can send you these results when we privately, if you want, later.
Maybe published after you publish after that.
I will published. It's very difficult to publish now. Okay.
Yeah, I know. Okay, thank you very much.
Thank you.
Yeah.
Thank you for the questions. Maybe one more. Okay, maybe I could ask one more before we go on. I have a lot, but I would ask the most general one. You mentioned solid solutions several times in the presentation. It seems to me you put some emphasis on those. Do you think, or maybe you have some data, how they influence, or do they influence the properties, the mechanical properties, to a significant extent, and if so, how?
In my opinion, it influence, especially we observed it even for boron carbide. We also checked that silicon can diffuse into hafnium diboride. Hafnium didn't diffuse, but silicon and carbon can diffuse. And in my opinion, it increases. It is also the real reason, in my opinion, to increase the hardness and fracture toughness of the material. We checked it very carefully with Auger. We each sample investigated by Auger spectroscopy, by EDX analysis, and we everywhere observed some diffusion and interaction between elements. And in my opinion, it has effect on the mechanical characteristics of the material, not only on this resistance against oxidation.
Thank you. Thank you. That's really interesting because probably then engineering of those solid solutions could be the further steps to improve the ceramics.
Yes, thank you. I
As
think so. I agree with you.
Thank you
Thank
very
you.
much again, Professor Prichna. We have to go on with the schedule, and our next presenter is another friend of our conference. Unfortunately, because of the circumstances, we cannot have him offline, but we are lucky to have him online, Branko Matovic, Doctor of Natural Sciences, Scientific Advisor, and corresponding member of the Academy of Engineering Sciences of Serbia. He also headed the Center of Excellence for the Synthesis, Processing, and Characterization of Materials for Application in Extreme Condition. Dr. Matovic, or Professor Matovic, work is often on the intersection of many disciplines that touch ceramics. So, as always, we can expect a very interesting, perhaps interdisciplinary talk here, which is titled Comparative Study of High Entropy Pyrochlore, Structural Evolution with and Without Pressure. Professor Matovic, please, could you share the screen?
Can you hear me well?
We hear you, but if you can maybe adjust the microphone so we can hear you better, because the sound isn't great.
Okay, I will try.
And the image
is better now.
Yeah, the sound is good, but the image on your video feed is we cannot see you. We see just a color.
I saw in the beginning also the same problem. I don't know the reason actually.
Unfortunately, we will hear you at least.
Okay.
But could you open your presentation?
Okay, you have my presentation now. Can you see?
No.
No. Oh, strange.
Maybe you have sent it to us also.
I sent it already, this presentation.
Okay.
It's very slowly, sorry. No.
Так. Professor Matovic, we will open the presentation from our side.
Okay, maybe.
Just a few seconds, please.
Okay.
Okay, we can see the presentation. Can you?
Okay, I open my presentation. I cannot see. I don't know what's happened actually. Aha, okay, now I see.
Oh, great, great. So please start.
Okay, can I start? Firstly, sorry for this inconvenience, but I don't know. Maybe I'm guilty. It is a totally new laptop. Maybe I did something wrong. I don't know. Actually, I would like to thanks to organizer for this conference. It is my few times I already participated for this conference, and especially thanks to the Professor Tatiana Prichna, with whom I cooperate many years. I am Branko Matovic. I am coming from Belgrade University, and I will talk about the comparative study of high entropy pyrochlore, structural evolution with and without pressure. Please, can you next one? Because I cannot move. I don't know why. Okay. I will talk about the compositionally complex ceramics. Actually, it is a new class of materials. Actually, I will continue this solid solution already Tatiana told before. It is complex chemical composition about the relationship between multi-complex solid solution. Of course, entropy is always included. Analysis and application of pyrochlore-based ceramics. I will show you the synthesis of pyrochlore with a multi-cationic structure with 10 equimolar cations, and about the crystal stability on high entropy pyrochlore under high pressure, some theoretical modeling, their structure, and of course my experimental work about densification, some characterization, and conclusion. Please, next one. Okay, when you're talking about the compositionally complex ceramics, this is their composition consists several elements in equi-atomic proportions, and complexity is based on Gibbs free energy, which is given by equation 1, and Boltzmann formula for entropy equation 2. Actually, all these G, S, S, K, actually it is the normal meaning. Usually all people know about this from science. But sufficiently at high temperature, the term in equation 1, where the entropy is determined from equation 2, dominates the Gibbs energy, thereby contributing to thermodynamic stabilization on singular phase. Please, new one. Okay, actually, this is the concept of high entropy oxide. In conventional oxide materials, the crystal lattice is typically formed by one or two different elements occupying specific crystallographic position in crystal lattice, of course. However, in high entropy oxide, as well as in the high entropy pyrochloride, multiply elements usually have at least five or more, occupy the same crystallographic site in achromatically equal proportion. This composition and complexity leads to a significant increase in configurational entropy, which contribute to stabilization of single phase structure. Okay, you can see the configuration entropy according to the Pauli expression. All people know about this. Okay, please, new one. Okay, thermodynamic stabilization of this, actually the formation of single solid solution high entropy pyrochloride is governed by balance of entropy and enthalpy, and is the contribution to Gibbs free energy. In traditional binary oxide, enthalpy plays dominant roles, and phase stability is often limited at high temperature due to insufficient entropy. But in contrast, in high entropy pyrochloride involve multiple elements in the different sites, leading to a significant increase in configurational entropy, and this relative entropy lowers the free Gibbs energy at high temperature, stabilizing the solid solution even in the enthalpy contribution is slightly positive or marginal. Okay, what do we have in the result? The single phase structure becomes thermodynamically favorable even in the system where phase separation would occur under classical rules, and entropy stabilization actually is the core principle in designing high entropy ceramic, and it is visually represented by the Gibbs free energy diagram comparing binary and high entropy system. Please, new one. Okay, in this diagram, I would like to show the mixing entropy as a functional number of component in high entropy materials. This means that adding more elements from 2 to 5, for example, or more, logarithmically increase the entropy, which can lead to the thermodynamic stabilization of the device metastably on a stable phase. This principle is central to high entropy materials such as oxide, carbides, borides, or actually more almost all composition where multiple cations are introduced on a given sub-lattice. Please, new one. Okay. Then the definition actually is based on the entropy, where high entropy materials have a configurational entropy greater than 1.61 R in their random states, where R actually is the gas constant. Okay, how we divided the poor compound with the S is about 0, low entropy, with the S which is less than 0.69, component medium, and compound high entropy. Higher entropy actually is the S is the bigger than 1.61. Please, new one. Okay, what do we have in multi-component phase diagram? In the left side, actually the schematic Turner diagram showing regions of the well-known materials near the corners and edge, and the region of poorly known and known material in the central part. It means that we don't know many things actually, just in the corner. And the right side of diagram, we have the traditional materials with this in the corners, equimolar materials in the middle, and a huge proportion of non-equilibrium materials. It means there are many, many materials that actually should be explored. Okay, new one, please. Okay, now I'll show this how it works in the pyroclast ceramics. You know, pyroclast ceramics is a very huge family of the composition of general formula I2B207, where in A position can be 2 and 3 valent, and in B 4, 5 and 5 valent elements. The structure represents a derivative from the Fourier superstructure of the two structures, where A, B cation arranged along the 1-1 direction in the space group 2-7, which is very close to the disordered Fourier structure with the 2-5 space group. All atoms occupy specific position, the two cation size, 3 anions, and anion vacancy at 8-1. Okay, I show how it looks like this composition, and some application of this very interesting compound actually is thermal conductivity, nuclear waste storage capability, neutron exhaustion, ionic conductivity, magnetism, luminescence, photocatalysis, and many, many the other properties. Please, new one. When you're talking about high entropy versus conventional pyrochlore, in high entropy pyrochlore, we have solid solution with multiple principal cation A, B size stabilized by high configurational entropy. In conventional pyrochlore, solid solution or other structure with few cation space typically optimized for the specific property. In high entropy pyrochlore, we have high stability and relative temperature compared to conventional, greater resistance to radon damage, reduce the diffusion and low degradation rate compared to the conventional pyrochlore. And in the conventional pyrochlore, it is very narrow stability field, but in case of the high entropy pyrochlore, we have a broader stability field in the pressure temperature diagram, and potentially improve mechanical property for the high entropy materials. Please, new one. Okay, in experimental work, we started from the pyrochlore structure where we have 7 different elements in position A and 3 in position B side. How we prepare this? We starting from the metal nitride using the 4 metal chloride, using the glycine. Actually, it is classical from the liquid phase and combustion reaction. And the results of this, actually, you can see the composition actually with how it is very huge. It is the same micrograph with corresponding this mapping of the synthesis, this compound, which is calcinated in 600 degrees for 2 hours. Actually, I don't know, can you see well, but it is very good distribution of these elements, very homogeneity. New one, please. When you got this material, it is amorphous because we calcinated in different temperature of 6, 9, 12, and 1500 degrees C. And you can see the phase evolution from amorphous directly to pyrochloride structure. The little refinement is done for the 9, 12, and 1500 degrees C. You can see the lattice parameter actually is the double compared to the fluoride structure. The crystalline size very low, very small particle size. It is about 900 degrees. It is about 7 nanometers, increases to 65 in 12. And of course, in 1500 degrees C, it is more than 300 nanometers. In the other side, strain actually decreases with the better ordering of the crystal structure and the higher temperature. I just show one sample of refinement structure for the composition, for the calcinated powder in 1500 degrees C. And also what is the very important, it is the oxygen coordination. To be a good high entropy compound with good stability, the oxygen coordination should be between 131 to 133. And in this case, we got, for the old our composition, good stability of this compound. Please, new one. Okay, this material from 900 degrees C, we actually sintered to get the pyrochlor ceramics, and sintering is done in normal atmosphere in 1650 degrees for 2 hours. And actually, this is a little refinement high entropy ceramics, which is obtained according to this condition that I mentioned. And some, you can see the structure, it is 227 space group, parameter actually is 10.57. What is very functional parameter for oxygen is 0.33. It means it is good stability according to this. And actually, we got the highly ordered structure. Please, new one. Okay, it is a micrograph of this sample, synthetic sample. You can see how it looks like the microstructure of this sample. And the EDS, I mean the elemental mapping, which is done for each element, actually show very good homogeneity for the whole sample. Entire sample, it seems, it is very, very homogeneous with all these elements that we introduce in the crystal structure. Okay, in the right side up, we have the high-resolution TM image of 2 peripheral grains. I hope you can see the bar is 5 nanometers. Actually, we would like to know what is getting in the grain boundaries between 2 grains, per peripheral grains. You can see very clean grain boundary without any secondary phase. Actually, it means that we have very clean everything, which is very good for some application in the higher temperatures. Please, new one. Okay, to be sure, again, we did the Raman spectrum synthetic sample. We did 15 measurements. In the insert up, we can see the value of measuring point distribution of the sample surface. And all these bands actually belongs exactly just to pyrochlor compound. Please, new one. Okay, we measure for this sample thermal conductivity and diffusivity. It is sample sintered 1600 DC, and you can see in the both case very low values for the all, let me say, measurements. Please, new one. way. For us, it was very important to know the crystal stability of this compound in high pressure, because we have many elements inside, and the question was what will happen if you try to press this sample with a higher pressure. Okay, we started from 0.4 gigapascal till 25.8 gigapascal, and you can see there are no any changing, because the structure is very stable from this region that we use, and the calculated lattice parameter and volume actually just show the decreasing the lattice parameter due to the high compression during our measurements. Please, new one. This is DFT calculation of the high pressure dependence of cell parameter high entropy parachlor, and calculation performed using LDPZ functional. And actually, we saw that our calculations for the experimentally results differ less than 1%. Actually, we got a good result for this. Please, new one. Okay, this is the modest multi-component high entropy parallel structure created with the PCA and supercell method, relaxing with the APZ functional, and actually atom is marked with different color. Y is the oxygen with the red one. You can see comparison structure, but very ordered with this composition. Okay, new one. Oh, already conclusion. Okay. Actually, we did a parallel compound prepared with this saffron rare earth continuous in A site and 3 different metal cations in the B site with the equal number of atoms. Actually, the X-ray show the sample is amorphous after the is prepared in this way. To induce crystallization, we did some sequentially calcinating different temperature from C to 1500, and results show the single phase parachlor structure is forming after calcination already 900 degrees C. The density of this ceramic is between 97 and 98 according to theoretical density, and it is produced from 1654 hours. And I didn't show result from the hardness. It is 8.3. Actually, hardness, I'm talking about the weakest hardness. And the measured thermal conductivity, it is very low. Actually, it is lower than the stabilized zirconia, which is actually the reference material for thermal protection. In the end, the high pressure behavior of this material show good crystal stability, indicating the potential application under extreme operating condition. Okay, I would like thanks again for invitation, and sorry for inconvenience, because I was very absent last time, and I am not sure that I am on time or not.
Thank you. Thank you, Professor Matovic, for a very interesting presentation, as always. It's actually a very attractive direction and area still. If perhaps high entropy alloys, traditional metallic alloys, are getting a little bit cooler, let's say, in interest, oxides and borides and other inorganic compounds, let's say, they are getting still more and more interesting, and that's why your presentation is particularly interesting and has a great actuality. Are there any questions in the audience? Yeah, please. Could you take a microphone, please?
One. Good afternoon. Thank you for this interesting presentation, in particular introductory section, which presents a very clear idea about the principle of high entropy alloys. And I would like to ask a question about the Raman spectra. Is it
Okay.
known which vibrational modes they contain and how to interpret them? Thank you.
Okay. The Raman which is done actually that I show here, actually all of this I don't know now. I must see the results to show you what is exactly the vibration mode which belongs to each group. But generally, I can say that it is actually all of them, of these modes, belongs just to the pyrochloride structure. Only they are changing little in intensity and though. Actually, there are no shifting of this.
Okay. Thank you for
Maybe
that.
it will be interesting. I didn't mention, I don't know here about the time. Probably you know for the Strangling approximations in mathematics. Actually, we try to calculate it how many the entropy materials can exist according to the number of elements, the change in their concentration, and so on. And we actually calculated using just a half of the elements of periodic system, not all. And we got the incredible results. Actually, more composition than in the Stein universe. It is from, we got some results about 10 on, I don't know, nearly to Gouglon number. You know, it is the biggest number which can exist. I would like to emphasize here the high entropy materials from the all has a very good potential for research in the future.
Okay. One more
Yes,
question from
to
the
your
audience.
explanation, but the line are a little bit broadened. They are very wide, and so
Could we
is it
perhaps go back to the slide so it's easier?
yes, it
okay,
would be
okay.
very helpful. Thank you. They are rather broad. So does it mean that this is they present some kind of?
Could you please stop the operator on the slide we need?
Here, this one. Yeah, the line is rather broad. Does it mean that they represent some kind of dispersion of various configurations within these alloy?
Actually, according to the pure pyrochlore, for example, we have just one element in the A and the other in the B, let me say, position. Actually, we compared with this one Raman that we got actually, the just position is the same. There are just difference in the intensity and the broad on the broad of the
density
difflection.
and probably in coordination, it also varies from side to side.
Yeah, exactly.
So,
I made mistake. I didn't put, let me say, what does it mean 3.7, let me say, which is the vibration from which group, let me say, in the structure, then will be clear. But I don't know, let me say now.
We have perhaps time for one more. Are there any more questions in the audience, maybe online? I would like to ask my own. And you mentioned non-equimolar compositions, and those are not very explored. I think one of the slides emphasized that. But as I understand it, entropy is going to be lower for mixed.
Sorry, I don't hear you. Can you hear me, please? There's some problem.
It seems that they lost connection.
Yeah, we lost for the moment
But
connection.
I hear you. Hello.
Hello, Tatiana. Again, no connection.
This trouble happened in institute. Maybe we will wait something from me.
Okay. Again, I don't hear anything.
But I think people who are online who hear you.
Okay, Tatiana, if we don't have connection, you can send me what do you like. I will answer very, let me say,
No,
carefully.
but I think that organizers better do this. Sure. Because I'm not in Kiev now.
I know now you are not in Kiev.
Professor Matovich, we the audience. We have. Yeah, please. Could you take a microphone, please?
One. Good afternoon. Thank you for this interesting presentation, in particular introductory section, which presents a very clear idea about the principle of entropy alloys. And I would like to ask a question about the Raman spectra. Can you tell which vibrational modes they contain and how to interpret them? Thank you.
Okay.
Again, I didn't hear properly. I don't know. It is some. Again, I heard a little and stop. Again, I don't know. I cannot, let me say, hear properly the question.
Наш параметр. Окей, мені надо код до конфи. Так, це другий же день, да? Оце от останні 20-40 останні, так? То код включив. Да, 20-40.
I'm called to institute. They try to reconnect for us, and they ask us to waiting because it's problem in institute something. And Professor Prichna, can I ask you about your presentation? Tatiana Prichna, Professor Prichna, you are here?
Yes, I'm here.
Tatiana, it's Hanna Borodyanska,
Yes,
because
yes,
we're waiting for reconnection with our institute. Maybe I can ask you one question about your presentation. You show the great results for 20 or 30% of silicon carbides. I want to ask, it's maybe will be for all elements of this group. I mean, it's zirconium, titanium, if you will put such
It's
value
between 20 and 30, yes.
yes, it's
We tried, no, how to say, it's in our conditions. In this particular, I don't know, maybe if you will make another conditions, it will be other data. No, you know this.
but in the literature is usually said is this value of silicon carbide. But I saw maybe it will be rule for this group of elements: titanium, zirconium, hafnium, maybe.
Colleagues, can you hear me? Can you hear me? I'm
Yes,
sorry
we are
to
here.
Hanna, Professor Prichna, I'm sorry to interrupt you. We have a little bit more serious problem here than we expected. So we connected from another laptop, and we will go on like this. I would like to thank once more to Professor Matovic for his talk, and now again, the timing problem. I would like to announce the next one. I beg you to excuse us for these technical glitches. I hope we will be back online fully in short. But now I would like to announce the next speaker. This is a younger generation, and with a computational work, which is, I think, fairly interesting, because the talk about selecting and discovering materials is old, and for many teams it is successful. But this, in this case, we will look at the attempt to discover some materials by similarity, just by using DFT, the results of DFT calculations from open databases of such data. And the presentation will be by Nazari Medyuk from Savage Institute for Problems of Material Science, titled Data-Driven Materials Discovery Using Density Functional Theory Data from Open Materials Databases. Please, Nazari, you have 15 minutes.
Yep. Hello, everyone. Let me share my screen and let's see if you can see it as well. Okay, let's go with the entire screen, I guess. Can you see my screen? Hello?
Yes, we can.
Okay, perfect. As Alexander introduced, I will be talking about the data-driven materials discovery using density functional theory from the open material databases. So this is really the plan of what we are going to look at. So first of all, about the databases itself. About the sorry, because I also want to share the slides on the here in the audience. Like we switched to completely different setup. Okay. Okay, great. So now it works. So this is really the plan of what I'm going to walk you through. So the first thing is about the data sources and how we parse the data. Then the data overview. So basically, what we will be able to was able to parse, and then the clustering itself. So how we try to find the different materials based on their similarity. But then first thing first, the databases itself. As you know, there are a lot of different databases such as Aflow, Nomad, Materials Project, and many more. And there is an attempt to have the universal API over those databases, which is the Optimate. So basically, Optimate supports around 20 different databases, and it allows you to grab the information from these databases as like in one go. However, the Optimate itself has, even though it's fast, it's simple, it has a lot of disadvantages. So you install the Optimate CLI and you try to count the structures in each of the databases and you immediately have the error. So the first command just doesn't work. And I tested that yesterday and it's still the case. So it just like doesn't work. You need to specifically exclude certain providers that doesn't support this command. And that's just one of the examples. So basically there is in Optimate, because they try to combine different providers and the providers itself store very different data in different representation. That means that there is a lot of inconsistency between the providers and Optimate just can't handle it properly. So there are random API errors, there is limited property availability, and there is limited access that is set by the providers. For certain technical reasons, providers doesn't allow to parse like more than 100 records, for instance, in case of Aflow, etc. So Then we tried to look for alternatives, and we switched to the Nomad API. So Nomad is probably the biggest database, materials database so far. It also combines information from Aflow, for instance, but then when they grab this information, then they completely convert it to their own format, and then the data that is stored in the Nomad, it is very consistent. Advantages, like we are using one provider, so we are facing only errors of one provider, not like 20 providers at the same time. Then Nomad have a lot of the data. It has the consistent format, and there is no artificial limits on the data access, so you can just like sequentially parse even the whole database if you want. However, it's quite slow. Nomad has two different APIs, the basic metadata that you can use to quickly see the results, and then the full archive data. It is much slower, but it contains the proper information about the calculation. Like in case of the DFT, it contains even like each SCAF step there. So basically, the rate of parsing is around 1.5 K records per hour, and that means that the like 70,000 structures that we parsed for as part of what I will be talking later on, it is only a couple of days, just like sitting and parsing them. So Nomad has very great like interface. You can go grab, check the properties that it contains, and then decide what you're interested in. And the first attempt was, okay, let's grab the properties and let's do the processing. Let's wait 2 days and then do something with them. But then we realized that we didn't include one of the properties in the parsing, and then we need to reparse again. And that's why we come up with a better flow on how to work with this data. So first one is we select certain materials. In this case, it was like 2 atoms, one of which is boron, and the second one is Ni. So boron star. Then we wait for, let's say, 30 hours, and we parse all available structures and store them in the MongoDB. And then from now on, we don't need connectivity to Nomad anymore. So basically, we own the clone of this data from the Nomad locally, and then we can do quickly like all the transformation that we need in order to do further analysis. This data went into 2 streams. One stream is for training machine learning potentials, which I won't be covering today. My colleagues were very busy with that, and just like a short spoiler, the results were not that good. So Owen DFT calculations were much better for the machine learning potentials for their training. But then we went a different approach. So we wanted to find the structures that are similar, like across all these boron star materials. We wanted to find some materials that are close to the boron carbide. That like moves us to the second part of my talk about the clustering itself. So these pictures on the right side displayed like various attempts to cluster the structures. Basically, we have many dimensions. And I will talk about that later. But the root problem was to figure out like what is the good clustering. And just by looking on projection on 2 dimensions, you can't tell like what is a good clustering or not, right? So like the top one seems reasonable, but then how that will help to find similar structures, it's really unclear. So then coming to the data, this is the features that have been parsed and have been used for the clustering. So we have the energy and equivalent stress. That is kind of like one data set. Then we have the second kind of like data set, it's structural, which is a space group, volume per atom, and then the geometry of the cell. Then we had the third data set, which is structural and energy and stress. And the fourth, like all features, which also include the boron ratio, second element atomic number, and second element group. So what that gives us, basically, that we split the features in the 4 different data sets, and we tried to apply the clustering on each of the data set to see how each data set performs, like what features are important for the clustering and what are not. Also, the considerations is that from these original 70K structures that we have, we do a filtering. So we looked only for the DFT records, and also we looked for the records that has all the properties that is listed in the features section, and we also removed the outliers. So that gives us around 30K structures that then we tried to cluster. So this is a quick overview of the clustering algorithms. I won't go through all of them, but mind that different cluster algorithms on the same kind of like shape will provide the different results. And that's why we try to apply different cluster algorithms that are marked as the like check mark to see how each of them performs. And now that said, we have 4 feature sets. We have 6 PCA options to reduce the number of features, and we have 6 algorithms. And for each algorithm, we have multiple combination of the hyperparameters, and that means that we have around like 2,500 attempts of a clustering. Each attempt provides the results that you see on the screen, and basically it splits all these 30,000 structures into clusters. And now the question, is this good? Right? This is the most complicated question that we had. So there are multiple metrics that we can apply. I will go through each of them. So that's the metrics that we were trying or considering. So the CLET score is the default metric for the clustering quality. It measures how well separated and compact the clusters are. So it measures the distance between each of the items of individual cluster, as well as the distance between different clusters. Then number of clusters. That is just the total number of distinct clusters found. So we want it to be reasonable, to be a reasonable number. So like if we have 1,000 clusters, it's too fine-grained. If we have 5 clusters, it's kind of like too raw. So we won't be able to find a good cluster. Then the size of the cluster, the just number of compounds there, then count of the boron carbide and count of a boron carbide in a range. So going back to the previous slide, this red line on the top, that is a target range for the boron carbide concentrations that we are looking for. So actually we were looking for the materials that are similar not only to like all the materials that includes boron and carbide, but we looked for the specific concentration range. So then like count of the structures in a specific cluster, then the concentration in each cluster. So basically that shows whether in this cluster we have only boron carbide or there are some other components. And we are interested if there are some other components because that gives us an ability to find the new components that are similar. Then the range purity, how much boron carbide compounds, like among boron carbide compounds, how much are in the target range, and then the capture rate. So we ended up with these 4 metrics that, and the total score was just the multiplication of these 4 metrics. And then the final result. So that's the best kind of like clustering that we were able to find. You can see the clusters that are marked as a group 16 and group 17. So from the right, the second and the third one, and you see that their like almost all the structures are in the target range, and like they seems kind of like reasonably good, whereas the other clusters are kind of like spread across all different concentration ranges for the boron carbide. So we achieved that by using the k-means algorithm, the feature set, which was all the features, and no PCA. Here, important to mention that also reasonably good results can be achieved with the energy and mechanics feature set. So like skipping all the information about the space groups, etc., like excluding from the data set, that still gives reasonably good results, but that was the best one. And here the information about these two clusters. So the first cluster, it contained mainly alkali and alkaline earth elements in combination with boron, and the second one is kind of like mixed, so there is oxygen, hydrogen, etc. But even like by the raw look on these like definitions of the cluster, you can tell that we were able to successfully separate like different chemistries in the different clusters, right? So that said, the conclusions are that the open material databases are a great source of the data that can be used for the various purposes. They obviously lack consistency because anyone can push their calculations there. However, with the proper filtering and proper data processing, you still can try to use these data for like analysis and manipulations. And then the idea, like, can we just like by using the clustering, can we find the materials similar to the boron carbide? Technically, that was validated. So we were able to find the approach that allows you to automatically find the good kind of like clustering candidates according to the metrics that we like introduced. So on the best result, as you saw, we found two groups of the structures similar to boron carbide that have been identified among available boron star systems, and that's it. Thank you very much. Yes, you have. Should I mute myself here? Okay. Muted.
Hello, one. Dear audience online, can you hear us now? Because we seem to have solved the technical problem. Can you confirm hearing me?
Yes, we hear you very well.
Hello, online audience.
We hear you very well. We hear you.
They can hear, but there is no
sound
output.
going back.
Yeah.
So
We hear a very nice
Немає
presentation.
just a moment before we start the discussion. One final touch, probably. Okay, maybe there are some questions in here in the offline audience. Can you pick up the microphone, please?
Is there any demo version of this your platform? I think this can be called platform. Just to try, because it's very difficult to explain just in words how it works if you don't have the access to try it.
My machine, so it wasn't published in any reasonable way. So, but that can be considered again. But it's not something that you can like go and try out at the moment.
The access to these databases, is it free?
Yes, it's free.
So anyone can just type Nomad. And,
Yeah,
just put into-
I would suggest to type actually nomad-lab. That would follow you to the specific project, because with Nomad you will see different sources there. So Nomad Lab would be the best search candidate.
Okay, thank you. Are there any questions online? Руки поднимите.
At least on my machine, the sound is on. So probably no question.
Okay, if there are no questions, unfortunately, I cannot ask any follow-up questions as a co-author of the of the report. So with that, we will thank Nazar Imenyuk, present him with a certificate of participation because he is offline. For the online participants, we will send them off by email. Sorry, not email, but by regular mail. And let's move on with the schedule. Our next presenter is, according to the program, it was Dmytro Zhivnyak, but it was unfortunately a mistake in the program. Dmytro has a poster presentation today, and thus the next talk will be done by Vladislav Bili, a PhD student from Francevich Institute for Problems of Material Science. And the talk is ab initio modeling of failure mechanisms in aluminum-doped boron carbide under uniaxial compression. Is it all? Looks at me. Not to... Vale. So. Не запрацював.
1-1.
Okay, so we are finally technically ready. Vladislav, please.
Yeah, okay. Is it work? Oh, can you share my presentation? No. Ну, шнурком це капець просто. Я буду їхати, я куплю нормальний. Так, а я не бачу презентацію. Я можу розказувати питання.
Ти онлайн.
Maybe you can sit near the computer and see your presentation, because we hear you and very nice sound, and we see your presentation in online.
Okay, dear symposium participants, as it seems, the technical problems we have are a little bit more difficult than we expected. So I suggest we move the coffee break a little bit. So let's do a 20 minutes pause until 11:30 and go back to work from 11:30 on, starting with the presentation of Vladislav Bili. I hope there are no objection about that. Please, online audience, confirm that it's okay. So 11:30, we are back. Hello? Hello? Online audience, can you hear me? Please confirm that.
We hear you.
Yes, yes.
Okay, great. So let's resume our session after the coffee break, and we will go on more or less the same as it was planned in the conference program, in the sense that the next presentation is going to be keynote, and after that we will go on with Oleksiy Bystrenko's speech and so on according to the program. So let me, with a great pleasure, present our friend, a friend of our conference, who is always caring and always helps and always present and always practically at each edition of the conference gives speeches in one form or another. These are all the time excellent speeches. Professor Oleg Vasylkiv from National Institute for Material Science, Japan. Professor Oleg Vasylkiv actually started his career here in Ukraine in Kyiv Polytechnic Institute, and then moved to Japan to go on with his excellent research. And today he will give a presentation titled Deformation Resistant Ultra High Temperature Barytes. Professor Vasylkiv, please, if you could. We can already see the slides.
Not
please
slides.
go on.
Okay. You said that it will be other presentation and screen. Okay.
Unfortunately, because of these technical difficulties, we have a little bit scrambled situation here. But I'm sorry, not interrupting. Please go on.
But I did not open my slides yet.
Do we have them open here?
Onto meeting. You too quickly change plans. Very difficult to keep your temp. Is it okay now?
It seems to load. Okay, so we see the interface.
Yes, now should be okay, yes?
Yeah, we can see everything.
Okay. Hello, everybody. Today, my talk title is Deformation Resistant Ultra High Temperature Barytes. I am Vasylkiv Oleg, and from National Institute for Material Science. Why do we need... Okay. Why do we need high temperature ultraceramic, which is a material for extreme environment, because ceramic with high thermal conductivity and operational temperature are unacceptable for metallic alloys due to creep oxidation and ablation process. Such materials are very useful as the leading edge components for aerospace, for example, hypersonic, for plasma-facing parts, for different parts of gas turbine, and for solar towers like a grid, superheater, reheater, evaporator, steam turbines, and condensers, and many, many other things. The demand for new ultra-high temperature ceramic is rising, particularly those that are multi-purpose, deformation resistant, and offer special protection for engines and vehicles. That's why the goal is to make a new ceramic composite class with exceptional well-balanced combination of strength, toughness, hardness, and modulus. Today, I will discuss preparation and properties of zirconium tantalum multiboride, tantalum monoboride, diboride, niobium diboride, and medium entropy 3-metal diboride. Here shown that monolithic carbides and borides without additives is required, but they are most high temperature materials. Borides and carbides especially need the consolidation temperature more than 2,500 degrees C, which is 0.7 melting temperature. These suggest that consolidation temperature should be like this one, or in case of spark plasma sintering, at least 2,200 degrees C. Why spark plasma sintering? This slide shows just like a schematic of processing, composition, structure, and properties. By SPS, reactive or non-reactive SPS from different starting powders, mixtures, or single material powder, we can produce very, very different structures. And finally, because structures and composition and grain boundary structure gives us different mechanical properties of material. As I say, the first part of my presentation will be devoted to zirconium tantalum multiboride preparation. Initial component were all commercials, zirconium diboride, amorphous boron, and tantalum metallic powder. The very, very interesting and important part is preparation. Preparation was a two-step. The first step is a mixture of tantalum with boron, and then mixture with zirconium diboride. Why it is necessary? Because on these schemes shown that amorphous boron mixed with tantalum, giving tantalum monoboride and tantalum diboride. During heating, the tantalum here is tantalum metallic and tantalum monoboride buffer. And during cooling, tantalum tetraboride with some non-reacted boron and tantalum monoboride solid layer. And zirconium diboride also takes some boron from here. And that's why zirconium diboride synthesized, and also zirconium monoboride and zirconium tantalum diboride solid solution. During heating and during cooling, the zirconium monoboride makes such a protective layer on the surface of zirconium diboride. This is an optical micrograph of supercomposite with a chain cell-like structure. You see that very reproducible in microstructure. And next slide show what is the composition. The composition, as I say, the tantalum zirconium, zirconium tantalum diboride, zirconium diboride, tantalum tetraboride, boron, tantalum monoboride, and zirconium monoborides. And the tantalum tetraboride around 10 micrometer clusters with an entrapped crystallized tetraboride with boron self-assembled into the short rod grains. Tantalum monoboride here, serve as a porous interlayer during the high temperature range, but similar to zirconium monoboride, it's formed dense 2 to 5 micrometer layer covered the tantalum tetraboride. And tantalum tetraboride and two binary diboride solid solution acts as a composite matrix, where the fine zirconium monoboride, zirconium diboride is quasi-continuous fibrils acts as a reinforcing phase. What we get using that interesting composition? This material shows the super hardness. Why super hardness? Because the literature data, a lot of literature data for 1 kilogram load shows the hardness around from 30 to 20 gigapascal. But in our case, in 10 kilogram load, material shows around 30 gigapascal, and in 20 kilogram load, it shows around 22. And also very reasonable fracture toughness. More than 4 megapascal. Then we check the room to high temperature strength, bending strength of that material. At 2000 degrees C, multi-boride composite showed a strength of 400 megapascal and fractured in elastic manner at the loading rate of 2.5 millimeter per minute. All these graphs, stress to strain, show the deformation under the very slow load, 0.5 millimeter per minute. But this curve show the 2.5 millimeter per minute, which is very rapid. And you can see that also elastic, and only 0.5 millimeter per minute at 2000 degrees C show the plastic deformation. And this level of strength is usual for the bulk zirconium diboride at room temperature, but this is at 2000 degrees C. And here, the representative fracture of the multiboride during the flexure at 1800 degrees C. There are some quasi-lamellar subgrains, mainly at the interface of tantalum tetraboride, and fracture at 1800 reveals only the presence of fine tantalum tetraboride fibers. And we deeply studied the fracture details and effects of the loading rates at the flexure at 2000 degrees C. And the strengthening toughening mechanism was proposed, which consists the crack tip deflection, micro crack tip shielding, and the crack bridging on that material. The next part of my talk, the describing of preparation and analysis of tantalum monoboride. Two approaches were used. The mixture, using SPS of mixture of tantalum, metallic tantalum, and boron, and reaction between tantalum diboride and metallic tantalum. The different composition and different consolidation temperature and consolidation condition were used. And by XRD was found that the preparation of boron with tantalum diboride at 2150 degrees C on argon media gives the best almost 100% tantalum monoborides. Mechanical performance of tantalum monoborides was studied using the samples prepared on that conditions, and you can see that hardness at 1 kilogram is more than 20 gigapascal. And the most interesting is indentation fracture toughness of this material, which was shown almost 10 megapascal under the load of 20 kilograms. You can see here the stumps, the cracks, and this is the data. Flexural strength of tantalum monoboride gradually increased from room temperature up to 1800 degrees C. And even at 2000 degrees C, it's also bit same as at 1800 degrees C. Also interesting phenomena that only at 1800 tantalum monoboride had loading curves exhibited non-linear characteristic associated with flow healing and plasticity, microplasticity contribution. And only after 1800 degrees C start the plastic deformation of this material. But you can see that material not as usual decrease the flexural strength with temperature, but increase. It means that material is deformation resistant. And short summary is that this first study of preparation 100% dense tantalum monobarite allow to produce material with very reasonable properties, and this graph shows the flexural strength of tantalum monobarite in comparison with zirconium diborite. The deformation resistance of ultra-high temperature ceramic and flexural strength sensitivity to the loading rate at elevated temperature. Here table shows the different cross-head rate from 0.5 to maximum is to 4 millimeter per minute. And dense tantalum diborite with a grain size range from 3 to 7 micrometer was SPS'd, and then 3-point flexural strength was measured as a function of temperature up to 2000 degrees C. And the strength exhibited deformation resistivity from room temperature to 1800, and above 1900 degrees C, the strength becomes sensitive to the applied loading rate. And in comparison, even at 2000 degrees C, the tantalum diborite shows the flexural strength around 400 megapascal, which is 200% from zirconium diborite. Sorry, back. Oh, okay. And this graph shows the high temperature strength and plastic deformation by behavior of niobium diborite. This work was done on almost 10 years, 9 years ago, and published 8 years ago. And the room temperature strength of niobium diborite was for 400 megapascal and remained constant up to 1600 degrees C. At 1700, it increased, not decreased, but increased, which is, and 1800 and up to, it still increased. And this was abnormal behavior for this year, for 2016 year. This was very abnormal behavior because usually titanium, zirconium, and hafnium borite and diborite properties decrease, not increase. This is this data. And this is usual previously published data for zirconium diborite and hafnium diborite. And as I said, that this material sensitive not only properties increase with temperature, but also the properties increased with a different loading rate. Here shown that depending from loading rate, with high rate deformation gives not lower properties, but higher properties. And one possible description of this phenomena, because that at first this material is very clean, that's almost no additives and no impurities during the consolidation. And the second one, that grain size is fine as possible, and that's why grain sliding and grain boundary diffusion allow to keep the properties high. Okay. Also, we try to produce high entropy, but finally produce medium entropy zirconium, hafnium, tantalum, equimolar diborite. And it shows very interesting, very good room temperature properties, but we did not make high temperature properties of that material. The last part of my today's presentation is preparation of medium entropy zirconium, tantalum, niobium diborite. The optimum creep resistance in binary solid solution always outside the equimolar composition. Rare studies focus on finding an optimum composition with the required set of material properties. That's why to evaluate the properties of zirconium, tantalum, niobium diboride, we produce not equimolar, but 3-2-1. 3 zirconium, 2 parts of tantalum, and only 1 part of niobium diboride. We prepared specimen by SPS and studied by 3-point bending test. But exploring ternary medium entropy, this system allowed to create solid solution of diboride to improve the set of properties at elevated temperature. Here, different compositions were produced, and the set of properties, this is flexural strength at room temperature, Vickers hardness, and fracture toughness of all these materials of different composition. And after close, you can see that not equimolar is the best. And after close inspection of the data, it was decided that zirconium, tantalum, niobium diboride with such composition should be evaluated as it had the strength above 800 at room temperature and the finest grain size after spark plasma sintering, after consolidation to full density. Here we analyze the flexural strength from room temperature up to 2000 degrees C. This is medium entropy diboride, and this is to compare with zirconium diboride. You can see that room temperature is more than 700 megapascal. At 1000 degrees C, it's still almost 100% better than for zirconium diboride. At 1400 degrees C, when zirconium diboride already goes down, it's still 50% higher. And then, of course, at 1600 degrees C, the flexural strength goes down, but around 2000, it becomes same as zirconium diboride. But just little advertising. This study is 2 years old, and on Friday, Professor Badika will describe our newest study, multi-phase 4-metal diboride high entropy material with a deformation resistivity up to 2000 degrees C. Please come and listen his presentation. And of course, I want to say thank you to my collaborators with whom I did this study. Professor Nishimura already retired, Professor Yashibi already retired, and this professor not retired, but retired from this team. This is Dmitro Demirsky, who also graduated from Kyiv Polytechnic Institute and then got a PhD on Frantsevich Institute. Frantsevich Institute, but he changed topic and now he works on different field. Thank you very much for your attention. Hello.
Thank you very much.
Okay.
Excellent review on the on
I
several.
hear you very bad.
Can you hear me now?
No, yes. Yeah. The main idea, if you hear me, it's okay. That's
we can hear you too. Thank you very much for a great report. I hope there are some questions for discussion. Are there any questions here in the offline audience? Maybe online?
I have questions.
Please, Dr. Bordyanska.
Thank you very much for your nice presentation. I have one question. What difference between medium entropy ceramics and high? It means only calculation of elements or some what?
No. Most funny that, as I say, that on Friday presentation will be multi-phase high entropy. This means high entropy, that is a solid solution, but that's many different solid solutions will be inside. And medium entropy is kind of still not single phase. many phase, but it means not all material is in solid solution. This is the main difference. Actually, how we start indicate medium entropy when reviewers review our papers, which 5 years ago was written high entropy, blah, blah, blah. They ask, but this is not a single phase. Please write medium entropy. And from that time, we start, when it's not really single solid solution, single phase, we write that medium entropy. But it's still solid solution. And it's not a multi-phase material. I believe I answer your question.
Okay, thank you. And I have one more questions. Did you see in microstructure after your proceeding ceramics some region with no diborite zirconium, no diborite titanium? I mean only zircony and only
No metals.
Only
Yes.
only
It can be
elements.
It can be carbides or borides, can be monoborides, can be tetraborides, but not metal. I understand your question that is it boron disappear and it's only metal? No, we did not see this, but it doesn't mean it don't exist in total. We did not see.
Okay, thank you.
Are there any questions in the audience or maybe online? If there are no other questions from the audience, I would like to maybe ask several of my own, I would like to go on to the medium entropy question, because now I need a clarification after Dr. Borodanska's questions. So it wasn't a single phase solid solution. What was it? The medium entropy, zirconium, tantalum, niobium, diborite. If it wasn't a single solid solution.
But initially I showed that high entropy should be the equimolar, or yes, as I remember. And this material is not equimolar. We definitely decide that one component should much exceed other components, and we just decided that it's still solid solution, but not equimolar and not. Yeah.
The entropy is not highest. In that sense, it's medium entropy, or
Yes. But as I say, 3 years later, we produce material which is, let's say, it's Badika will kill me, you know, that's because I am now saying what he will say on Friday. But anyway, I will say shortly. By XRD, it's single phase, high entropy. By SEM, it's single phase, but not very uniform distribution of component. And when we go on TM, then on Friday you will see what happened on TM, because that show very, very different. But still on XRD, it's a single phase, high entropy material. And in case of this medium entropy, XRD show also other phases, some not so many, but other phases. And that's why that is not, for reviewers, that was so. Is it good or bad? Is it good or bad? I can't say.
Were you able to see what those other phases were?
We see and we write, but I don't remember now. If you read that paper, that script, if you want, I read for you.
Thank you.
Okay, I really don't remember. Yeah.
If I may, one more question, follow up to that, which is you showed the more or less old work from 2017, I believe, where niobium diborite shows strength at high temperatures.
No, only at room temperature. That one I show that it's only at room temperature. Wait, I will. Oh, okay.
Uh,
No, not here. Wait,
Ivan.
wait.
Ivan.
Yes, high temp. Yeah. You're right. Yeah, high temp. Yes, and your question.
Yeah, with niobium, we see strengthening here. And
I already
as I
opened that
understand it,
slide.
for the medium entropy solid solution zirconium, tantalum, niobium, we don't see the same picture.
Okay, nice question. I always like it. I can say that two metal diborides, not single metal, two metal diborides usually show much better properties than single metal diboride. But high entropy material until last year, I always say that high entropy gives also properties which much worse than single metal diborides. And only once we produce ceramic with properties which are not worse. And that, do you see now my slide or no?
Yeah. We see the slide currently.
Okay. What I mean that this is single metal diboride. It shows excellent properties. Usually single metal diboride show such properties, and high entropy usually show also decrease in properties with temperature. Only because of grain size, because of grain boundary microstructure, and many other things which Badika will describe on Friday, we could produce the ceramic which show good increasing of properties to 1800 and then little bit decrease, but still very good. But that properties much worse than single metal diborides. You understand my answer?
But much,
properties of high entropy ceramic in absolute value lower than single metal diborides.
Okay. So.
And this is my definition, my personal definition. And what we now only succeed that we made, I just show you, we made a deformation resistivity, mean they don't go down, but they are not better than single metal. I don't show this graph, I just show you line, not on this graph, just somewhere here. Please go to his presentation and listen about that.
Okay, thank you very much. I try to be there. Any more questions? Thank you very much, Professor Vasilkiv, for your great presentation. Let's move on with the schedule, with our program. And the next speaker will be actually from the sections that should have been before the coffee break. Dr. Alexey Bestrenko from Fransevich Institute for Problems of Materials Science. He will give a talk first principle study of B12 based orthorhombic metal carboborides. Dr. Bestrenko, are you present?
I'm here. Do you hear me?
Yeah. We can hear and see you. Please share your presentation and you may start.
Okay. Good afternoon, everybody.
We cannot see the slides yet.
Yeah, I will just share my screen.
Can you try opening them? Oh, thank you. Go on.
It's okay? It's okay now?
Yeah. We can see them. Please go on.
So, good afternoon, everybody, and I'm going to begin my presentation. In my talk, I'm going to discuss the properties of orthorhombic metal carboborides, which do incorporate as structural units the icosahedra boron units. This work was carried out in cooperation with large number of co-authors. And here you see the team which participated in this work from Shanghai Institute of Ceramics and from our Institute for Problems of Materials Science. The orthorhombic metal carboborides belong to the family of boron-rich compounds which are based on boron icosahedral structural units. These compounds attract the attention of researchers because they exhibit typically number of valuable properties like low density, low mass density, high thermal and chemical stability, high melting point, and high hardness. Examples, well-known examples are boron oxide, boron carbide, boron sulfide. So these several examples are widely and intensively investigated. The idea of this work was to investigate the number of compounds which would be as structural to the compound magnesium carbon 2 boron 12, which belongs to the family of orthorhombic metal carboborides. Actually, as far as I know, is the only composition, or the only compound of that series, which was experimentally synthesized in the year 2007. And theoretically, it was shown that they predicted properties, mechanical properties, predicted properties are better, much better than the other representatives of the family of orthorhombic metal borides. Well-examined example is aluminum magnesium boron 14, which is very well investigated theoretically and experimentally, and has already found industrial applications and has much lower mechanical constant parameters such as bulk and shear moduli. Excuse me, is sound okay? I'm available. Is connection okay?
Can you hear me?
So now I hear you. Is everything okay with connection?
Yes, yes.
Okay, so I go on. So in this picture, you can see the comparison of these both structures, aluminum magnesium boron 14 and magnesium carbon 2 boron 12. They're very similar. Boron framework is actually very similar, except for one exception. the interstitial boron atoms which form boron network are replaced in carboborate structure by carbon. As on the left, these boron atoms are shown in brown, and on the right, the respective carbon atoms are shown in gray. Besides, the aluminum atom should be removed to obtain the structure of magnesium carboborate from the structure of aluminum magnesium boron 40. So the idea is to investigate the possibility of existence of series of isostructural compounds by replacing magnesium by different atoms of second and third group of elements, such as calcium, strontium, scandium, and yttrium, with close structure of outer electron shells. This work was theoretical, and it was based on density functional approach, which has proven to be reliable tool for investigation of such kind of problems, reliable and accurate tool. They used very well tested library of pseudopotentials in this exchange correlation in PBE form and using general gradient approximation. In this table, you see the calculated structure of these theoretically predicted compounds. Here, the only experimental observed composition is magnesium carbon 2 boron 12 and aluminum magnesium boron 14. All the rest below, these are theoretical predictions, and the numbers are the result of simulations of simulations aimed at finding the equilibrium accurate structure, space group symmetry, and so on. We see that the crystal system, space symmetry are very similar for all the series of compounds of that under consideration. Magnesium-based, calcium-based, strontium-based, and they have predominantly negative formation energy, which to some extent may evidence their relative stability. This table, we see that the lattice parameters are very close for calcium and strontium and magnesium phases, and the Wyckoff positions are the same, and fractional coordinates, which also evidences the similarity, structural similarity. Then using quantum espresso, using density functional theory, we calculated elastic constants. Here in this table, we see, and on the basis of these calculations, we can calculate bulk and shear modulus according to, for instance, weight averaging procedure. And here in this table, the results of such calculations are given. The results, the numbers for elastic moduli are Voigt-Royce Hill averages. So we see the most remarkable finding is that we observe very significant increase in isotopic elastic moduli, shear, specifically shear and Young moduli in these phases, as compared to conventional aluminum magnesium boron 14 phase and magnesium carbon carboboride phase. Also, magnesium-based carboborides also exhibit some increase of mechanical properties. This result suggests that the hardness should be also high, better at least. And to make estimates about the hardness of these compounds, we used 3 empirical models. Here are the relative equations, which are based on the correlation between the elastic properties and hardness, Vickers hardness. The results are given in this table. We see that according to these models of hardness, there are very significant increase for the predicted theoretically predicted phases, strontium, calcium, ethanol, scandium, as compared to more conventional known phases such as boron carbide, boron oxide, or aluminum, magnesium, boron 14. And this actually raises a question. Raises the question about the stability of these phases in order to, if they can exist as a stable phases. In order to investigate the hardness properties, it is important to have an idea of plastic deformations, of how these phases are their properties during the plastic deformation. Sorry. In order to study this issue, we performed a series of calculations for shear strain, examining the shear strain stress dependencies in different directions, and the result are summarized in this table on the right side of this page, which do show that the shear strains in most typical representative directions, weakest and strongest directions, are indeed much better, much higher than the aluminum, basically those of reference system aluminum, magnesium, boron 14. The mechanism of improvement of these mechanical properties may be that shown in this picture. There's a comparison of the changes during the shear deformation. On the left side, we see the shear deformation of aluminum, magnesium, borate, and we see how during elastic failure, we observe the breaking of boron-boron bonds connecting different boron layers. And on the right side, the same similar picture, similar simulations have been done, where we observe the breaking of carbon-carbon bonds connecting boron layers. And this demonstrates the role of this new type of bond, carbon bonds, in strengthening this theoretical predicted compound. Electronic structure also was examined, and according to our results, we see that the metal elements of second group exhibit the properties of semiconductor or insulators, whereas the metal elements scandium and yttrium of third group is slightly different structure of electrons, outer electron shells. They have an additional valence electron. They exhibit the properties of hard metallic phases, similar to the aluminum magnesium boron 14 compound. We see that Fermi level is located in conduction band, which shows that this compound should exhibit to some extent metal properties like increased electric conduction and so on. We investigated a very important question was to study the issue about the stability. Simple static mechanical stability can be easily established by using some criteria which are well known and which is based on comparison some relations implying some imposing some relations on the combination of elastic constants, and it's trivial. However, maybe more important is to investigate the dynamical stability. Dynamical stability means that the system should be stable with respect to excitation of any single mode. In the normal mode representation, normal for non-mode representation, this question can be answered by examining the Fanon dispersion curves. So we give the results of calculation of dispersion curves for calcium, strontium, scandium, and yttrium based phases under consideration. We see that the absence of unstable absence of imaginary frequencies, and which indicate the stability, dynamical stability of these compositions. Another way to verify stability is to directly examine thermal stability, which can be viewed as the generalization of dynamical stability at elevated temperatures. If we carry out molecular dynamic simulation at the temperature at the Dubai or higher temperature, we can observe the process, monitor the process of thermalization, and here are the result in these pictures for scandium carbon 2 boron 2 compound. Here we used the temperature of approximately 1500 Kelvin And on the left, we see the behavior of temperature, the thermalization, which is occurring at approximately 0.4 picosecond. And in center, you see the behavior of lattice parameters, which do oscillate near the average values, and therefore indicate the more or less stable lattice geometry. And on the right pictures, we see the behavior of angles, which do oscillate near the average value of 90 degree, which indicates that the crystal system remains unchanged, orthorhombic. To conclude, the simulations performed predict the existence of new family of superhot orthorhombic phases, carbon phases of the composition metal carbon-2 boron 12, where metal can be magnesium, calcium, strontium, scandium, and yttrium. All these compounds have the same symmetry group EMMA and similar structure, very similar. The important is that the thermal and dynamical stability of the phases has been established by means of both Born-Oppenheimer molecular dynamic simulations, quantum molecular dynamic simulations, and by examinations of phonon dispersion properties, as is now accepted as conventional way to check the dynamical stability. And the simulations, DFT simulations, evidence very significant increase in mechanical properties, like the numbers for Vickers hardness as about higher than 40 gigapascal. And these conclusions are confirmed by direct simulation of shear strengths for the weakest and strongest shear systems, which indicate also an increase up to 50% for several, in some cases, as with respect to the reference aluminum magnesium boron 14 compound. We can also point out that the mechanism of this strengthening is proposed, which can be explained by creation of interlayer carbon-carbon bonds, which are stronger than boron-boron bonds. In view of distinguishing mechanical properties, I think that this theoretically predicted family of compounds may be promising for creating novel superhard materials. The results were published in 3 publications.
Alexei, I'm sorry, but you are we are behind the schedule, so probably publications could be found in the internet.
I finished already. Okay, thank you. If
Perhaps
anybody...
one or two questions. Here in the audience, are there any questions to Alexei? Of course, please, Ivan.
I have a question. Do you hear me?
Yes, I do.
How do carboborides differ from other borides and carbides in terms of chemical bonding and electronic structure? Maybe I missed that, but have questions.
Okay, I will go to this. Usually, metal borides, such as titanium borides, which has, as far as I remember, hexagonal structure, or zirconium boride, they do form covalent bonds, and they are not bone-rich compounds, in the sense that the number of bone atoms and metal atoms in a unit cell is approximately the same or close, on the same order. This metal, orthorhombic metal carboborides or metal borides, orthorhombic, are based on the using structural boron icosahedra. Here we see it consists of boron layers. These layers consist of boron icosahedra. Each boron icosahedron consists of 12 boron atoms. So here the number of boron atoms is dominating, and the bonding of metal atoms in the structure is quite different. The metal atoms do ionize and donate the valence electron to the bond framework, and actually the mechanical properties of such compounds, we can see also this effect in boron oxide, which has a similar principle of building of structure. The mechanical properties of such structures are determined by the boron framework predominantly, not by the.
Okay, thank
Alexei, Dr. Bustenko, thank you very much. We unfortunately don't have time for two extended discussions here, and we have to move to the following presentation.
Thank you for your attention.
Very much for your report.
Thank you.
I think we will hear from you today again. The next presenter is Anton Bocharov from Iron and Steel Institute. Named by Nekrasov, National Academy of Science of Ukraine, with a speech, with a presentation clustering of experimental data on the properties of oxide melts for studying their structure. Dr. Bocharov, are you online?
I'm here.
Yeah, please share your presentation and you may start.
Yeah, sure. 1 second. Так. Поделиться share. Do you see?
Yeah, we can see and hear you, see the presentation and hear you well. Please start.
Okay. The properties of slag melts play a crucial role in the steel making process, as they directly influence metal quality and melting efficiency. Also, the service life of equipment. Understanding the physical and chemical behavior of slags is therefore essential for optimizing refining reactions, controlling inclusions, and minimizing refractory wear. Recent research has focused on prediction slag properties such as viscosity, electrical conductivity, and phase equilibria in order to improve process stability and energy efficiency. Consequently, accurate modeling of slag systems remains a key aspect of modern metallurgical engineering. The many models that attempt to predict the properties of slag melts, but they lack parameters that account for the structural features of oxide systems. In this example, software fact stage, what uses a modified quasi-chemical model to calculate the viscosity of melts and glaces. This model directly links viscosity to the melts microstructure, which is in turn calculated based on thermodynamic description of the system. How you can see below on the graphs, the dashed lines represent the obtained results. Solid lines correspond to the external data. However, it has shown significant deviations, particularly in the low temperature range. Despite various attempts by researchers to account of the structure of slag melts when predicting their properties, the problem remains unsolved due to a lack of fundamental knowledge. One possible approach to addressing this issue in the clustering of experimental data, which makes it possible to identify hidden relationship arising from the structural characteristic of slag melts. For a better understanding of this logic and structure of this work, step-by-step visualization of the algorithm sequence of stage is presented. Example, data representation, demonstration of slag chemical composition and properties data, data pre-processing, outlier detection, missing value handling, future scaling, selection of methods, Cummins and agglomerative clustering, hierarchical clustering, and finally conclusion. Now, in this report, I use Cummins method because it show better results than agglomerative clustering. This research data set contains a sufficient number of oxide system composition observation, 48 rows, 48 observations. Two properties are also included: viscosity and electrical conductivity. Measurements were carried out over a wide temperature range from 1400 to 1800 degrees Celsius, with a step of 50 degrees. These characteristics of the studied dataset make it suitable for comprehensive statistical analysis. And CO2 range from 30% to 60%. Magni or from 10 to 45%, and aluminum 203 from 10 to 50%. This ranges chemical components value. We can, as a first approach to identifying the relationship between the chemical components of the slag melts data, a correlation matrix was constructed. But for temperature at 1800 degrees. The upper right section of the matrix displays the non-partial Spearman coefficient correlations coefficients, while the lower left section present scatter plots for each pair of parameters. The Spearman correlation was chosen because the data are quantitative and don't require a normal distribution. No, and second, it's more robust to outliers and a non-linear relationship between chemical components. This partition show clustering visualization, but on the left side, cluster visualization of viscosity at temperature 1800 degrees. This using the clustering method, data set and divided into n clusters. In this case, into 4 clusters for the temperature, where the within cluster variance is minimized and between cluster variance is maximized. Also, we can observe on the right side how after clustering, chemical components is distributed within each clusters and their possible mutual behavior. Also, it is histogram of the chemical elements within each cluster for viscosity at temperature 1008 degrees. This correlation matrix, these figures follows the exact same logics as slide number 5, with the difference that the correlation coefficients and scatter plots are present within each individual clusters. This graph, together with the previous one, provides an understanding not only of the latent behavior of properties and chemical composition, but also a statistical justification. Also, during the study pattern was observed behavior of slag properties, the temperature decreased. Stable property behavior during the study pattern was observed in the behavior of slag properties as the temperature decreased. Stable property behavior was noted at temperature from 1700 to 1800 degrees, followed by the division into 4 clusters for viscosity. How can you see clusters has same structure and counts. Not structure, and the cluster has same chemical components and numbers. But with decrease at 50 degrees Celsius, when temperature is 1650 degrees, some elements moved to another clusters, and this first changes what we can see. As the temperature decreases to 1,600 and 1,550 degrees, not only the composition of the cluster changes, moved to another clusters, but also changed their numbers. And as these graphs show how method clusterization groups to cluster sample research data with electrical conductivity. And as can be seen, this with decreasing temperature changes our content values to different properties. However, it should be noted then that the dataset with electrical conductivity measurements is grouped into 3 clusters rather than 4 as the case or viscosity. Changes for electrical conductivity begin with temperature 1,650, like for viscosity. But number clusters for viscosity and electrical conductivity, the difference. It's very interesting also views. For electrical conductivity with decreasing temperature 1,600 and 1,550 degrees, we can see strange behavior with clusters. But we can explain this behavior. But in the future, we can research that more. And also 100. This clustering is possible to reveal hidden relationship between chemical composition, temperature, and properties determined by the structural characteristics of slag for each cluster. This will make it possible to take structural features into account when predicting properties, as well as to build models for multi-component system. So this work is dedicated to selection method that can largely highlight the hidden features in the behavior of chemical composition, temperature, and properties. So thank you for your attention. Maybe you have a question.
Thank you very much, Dr. Bocharov, for an interesting report. Are there any questions in the audience? Perhaps online? Yeah, we see a hand raised online. Please turn on your mic. I unfortunately cannot see the name.
Natalia, thank you very much. So you can hear me, or?
Yeah, we can hear you.
The sound is okay. Okay, I have 2 questions. First of all, thank you very much for the interesting talk. And I have 2 questions. The first one is about the metric. What kind of metric did you use for K-means clustering?
I used Euclidean metrics. It's best. It shows best results than Manhattan's or Minkowski.
Okay, thank you.
Euclidean.
Okay, so it's compatible with your data then. And the next question, I saw two axes, like the dimension 1 and dimension 2. What is the meaning of this axis? Because it's not the, I guess it's not the chemical composition, or this
Can you
X
repeat?
and
I
Y,
can't.
two axes?
Axis, can't understand.
Maybe if we go to the picture where you have your clustering, so your clusters on the slide.
Just 1 second.
Yes, maybe here. Like you have an x-axis, dimension 1, I think, and the second axis, so the y-axis is a dimension 2. What do they mean? What is the meaning of this axis?
This show what clusters have our cell structures and our components same the next temperature 1800 1750 degrees and 1700 degrees. With this temperature range, cluster has same no changes elements, no changes structures. But with temperature 1650, right low corner, right corner on the low, we can first changes in clusters. Same each elements, each chemical components moved to another clusters. So it's starting to changes into data with decreased temperature.
Okay, thank you. So the question was also about these dimensions. So because you have 4 components, I saw chemical components and different elements, like, and you have 2 axes, but maybe we can talk about that later. Thank you very much.
Yeah. But if decrease more than 1600.
Anton, I believe it's not the question, Anton. The question,
okay.
The question is why your axes are marked with some strange dimensions instead of physical features. Am I right?
Yes. Yeah.
I can explain.
Did you do the PCA maybe or something like that with your data?
I can't understand.
Maybe you done some kind of model, so reduction, dimension reduction technique, like PCA, maybe, yes, something like that. But it's interesting to know. But
okay.
Yeah, maybe we can speak during the coffee break. Thank you.
Yeah, you have a chance to do that, I hope.
Yeah, thank you very much.
One more brief clarification from me, if you don't mind. Viscosity clusters.
Yeah.
We see them, and then you showed the distribution of chemical composition of the components in the cluster and also viscosity values. Could you please go back to that slide? Yeah, here. So cluster 1 and cluster 4 appear to have more or less same viscosity. Is it correct?
Same viscosity, no. Maybe. But other this may be same behavior, but other chemical components. But one thinks cluster number 4 has a little a little count of chemical components.
Okay,
No?
I see. So my thought was the target was viscosity to some extent. Yes. So
viscosity,
we wanted
viscosity, yeah, behavior of viscosity may be same.
Okay, I see now. So the chemical composition differs significantly in those two. Thank you. If there are no other questions, let's move on to the last presentation in this session. Thank you very much, Anton Bacharov again.
Thank you.
And once more, Dr. Alexey Bystrenko from Frantsevich Institute for Problems of Material Science with the presentation general expression for the energy and the equation of state for polycrystalline solids. Dr. Bystrenko, please start, and I would ask you to keep to the timing, please.
Okay. Do you hear me? Is sound okay?
Yeah. We can hear you. Please share your presentation.
Oh, I'm going to start. In this talk, I'm going to discuss the very ancient question of equation of state of solids, which has attracted the attention of researchers maybe more than 100 years. At present, the importance of this question is in first place due to its fundamental meaning, and on the other hand, it finds applications in various sciences like geophysical sciences, where it is important to have an idea of the phase state at high pressure. At present, very large number of empirical relations, like P as a function of volume, pressure as a function of volume for solid materials is proposed, and most known are Birch-Mernigan, Gruneisen, Holzapfel, Vinet, and other approaches. One of the most frequently used is the third order Birch-Mernigan equation. It maybe should be noticed that the purely empirical approaches are mostly accurate for only some classes of compounds like metals or hard covalent compounds, while those based on the thermodynamics represent free energy and pressure in the form of a power series of strain parameter, and subsequently require high powers to be approach high accuracy. In this work, the idea is to propose another semi-empirical equation of state, which is supposed to be accurate for various types of compounds, polycrystalline compounds like metals, ionic and covalent crystals, and elucidate its relation of this equation of state to the classical elasticity theory. I will begin with reminders of basic relations from classical elasticity theory for small strains. It's well known that for an isotropic solid, in the case of small deformation, the elastic energy density of elastic energy can be represented as a form given in the equation 1. Here, it's based on using two scalar quadratic square invariants E sub B and E sub G, which relate to respectively bulk compression and shear deformation, bulk compression deformation and shear deformation. And since the only two independent quadratic scalar invariants can be associated with symmetric second rank tensor. In the case under consideration, we will consider only volume, non-shear hydrostatic compression of isotropic polycrystalline solids. And that's why the equation 1 can be simplified to the form given in the line 4, the equation 4, where the bulk modulus can be found from Voigt-Royce-Hill relations. For small deformation, in the case of purely volumetric compression of an isotropic medium, all the diagonal components of strain tensor are equal and can be denoted as epsilon in this case. And as we see in this series of relations, we can use the following strain parameters. The ratio of volume to initial volume in power 1/3 and C, which is equal to the invariant E sub B, which is equal to 3 times epsilon. As from what I said, it follows that we can write for the case of small deformation in the isotropic media, the relation for the energy, elastic energy, in the form given in the equation 5, which is in fact actually another formulation of Hooke's law. To this point, it was a well-known theory of elastic isotropic media for small deformation. However, from the considerations given before, it follows that due to similar consideration, we should expect that the elastic energy for arbitrary, large, non-linear, but elastic deformations, the expression should look as given in equation 6. And the function additional multiplier, the function phi of C should approach a limit 1 as deformation strength parameter C approaches 0. And the basic empirical assumption is just a wild guess of this work, that the elastic energy for isotrope and polycrystalline solid can be, in general, described by the function given in the equation 7. As the basic assumption, it means that we accept that the function phi has the form 1 over 1 minus alpha c squared. And from it, we can derive the equation of state by simple derivation by volume, and the result is given in the equation 8. The parameter alpha can be regarded as a fitting parameter, but it can be also determined from thermodynamic consideration, absolutely similar to how it's obtained when deriving Birch-Manneken equation of state. Namely, we can use a series of relations, thermodynamic relations, and from this, after a large number of cumbersome calculations, we can derive the result in the form given in the last, at the bottom of the page, as alpha equal to, etc. So we see we can connect alpha, the number of alpha, to the first derivative of bulk modulus with respect to pressure. And to validate this proposed expression, proposed analytical theory, we performed a number of first principle simulations for large number of compounds, inorganic compounds. These simulations were based on first principle density functional approach, and the parameter was used to provide a good accuracy, high accuracy. In particular, the energy conversion threshold was set 10 to minus 8 Rydberger. And below, I will show the results of this comparison. The notation which used in the pictures which follow are the following ones. Blue line is analytical theory proposed in this work. Yellow line is third-order Birch-Mulligan equations, and red line is quadratic approximation. It's in fact the formulation of one of the possible formulation of Hooke's law. And the square dots, these are the first principle calculations by density function. So we begin with metal, and I will go through this series of pictures. What here is displayed. On the left side, energy per atom in Rydberger, compared to the blue line is our theory. Square dots are first principle simulations. Yellow line is Birch-Mulligan, third order, and red line is quadratic approximation, Hooke's law. And on the right side is actually equation of state. The pressure as a function of parameter C, which can be related unambiguously to volume. It's a kind of equation of state. And we see that the first principle dots, square dots, do exactly fit the theory. Those equations which were proposed in this work. And then metal, copper, this cubic crystal system, and situation is the same. Then gold cubic crystal system, situation is similar. Ionic crystals, rock salt cubic, the same situation. Calcium fluoride cubic, also the same. We observed that for all the components, for all the compounds considered, the first principle results are perfectly reproduced by this equation, this analytical relations which we propose in this work. Diamond, covalent crystal, sphalerite, zinc sulfide, rock salt structure, alpha boron, trigonal crystal system, and even so, even we see that at the negative pressure, the coincidence, the agreement is very good. Magnesium carboboride, more complex structure with large number of atoms in primitive cell, and size is equal to 30. And topaz, orthorhombic crystal structure, and size equals to 36. In all cases, we observe excellent agreement with these first principle simulations, and it was interesting to test this approach, our relations at as investigating the pressure-induced phase transition. And we selected spheroid rock-salt phase transition and zinc sulfide, which is very well investigated, very well examined subject in large number of works, starting with maybe 70 years of last century. And on the left side here you see the behavior of enthalpy calculated by means of relations analytical, and its validation by the first principle simulations. And on the right side, we compare two enthalpies calculated from our theory for spheroid structure and rock-salt structure for zinc sulfide. And we see the point of interaction. It occurs at the pressure of 60 gigapascal. And as we see on the right side, the comparison with experiment shows that it's excellent agreement with experimental data available, which do range from 15.0 to 16.2. And the last most reliable result, I think, is from reference 6, most recent result. And we see that our relation describe perfectly this phase transition as well. So the conclusions are that the proposed semi-empirical relations 7 and 8 perfectly reproduce the results of first principle calculation in wide pressure range and up to 3 megabar for various polycrystalline solids, inorganic solids, with different type of chemical bonding, covalent, ionic, and metallic. In particular, we were able to perfectly accurately describe spheroid rock-salt phase transition and zinc sulfide. And as for third-order Birch-Monaghan theory, it better reproduces the behavior of covalent compounds, more hard compounds, and for less hard compounds, particularly those with ionic and metallic bonding, the Birch-Monaghan theory gives slightly underestimated value for energy and pressure. However, it should be reminded that it's only third order, and we can subsequently increase accuracy of Birch-Monaghan theory by taking fourth, fifth, and so on order of the theory. And to get an idea of how general the proposed theory is, and to find out the perspective of this approach, further verification at larger number of compounds is needed. So, thank you for your attention. That's all. If there are any questions, please.
Dr. Bystrenko for another interesting presentation. Are there any questions to the speaker? There are no questions. May I ask one? Perhaps it was in your presentation, but maybe I've missed. Just as a reminder, how many compounds or structures or even systems were used to validate the universal approach?
In general, here we present 12 as far as I remember, 12 structures. But in actual fact, we considered far more, about 30. But you know, if the theory is empirical, you never can be sure that that you can predict everything. It's just a matter of permanent verification. About 30 compounds, including titanium diborite, and some zirconium diborite, and some other which were not mentioned here.
Okay. So many and sufficiently diverse to call the equation now, or the approach now, universal or general. Yeah, general.
I'm not sure that, but it's an assumption. It's suggest it should be verified, of course, but it's a matter. This question can be addressed only by experimental verification or by first principle verification, and this question concerns as well the all other semi-empirical or empirical approaches like Birch-Manigan or Vinay, for instance.
Okay, thank you. If there are no more questions, we have completed the program for the Advanced Ceramics and Glasses Symposium. I want to express our gratitude once more for everyone who gave their speeches, their interesting reports, and to apologize for our technical failures here, though we cannot control them completely, but we are the organizers, so we are sorry for that. But we hope that further sessions will go on more smoothly, and we wait you here after the lunch at 14 o'clock for the low dimensional and nanomaterials session. Thank you very much, all of you, and until next time.
Okay, we will start, okay? Ми зараз перевіримо. Okay, ladies and gentlemen, dear colleagues, my name is Elena Lavrinenko, and I have honor to be the chair on the symposium of love dimension and nanomaterials. The head of our symposium is academician Andrei Ragula, but he had to be present today at the Presidium of National Academy of Science of Ukraine because of the election, the president of our academy. Also, on behalf of our organizers, I will say the greeting words and congratulate our participant and our guests. I hope your participation in the conference not only allow you show the result of your works of the wide Ukrainian and international scientific community, but help you to sort in the search of the potential partner for international communication and join the project. I would like to wish you the good and interesting work in the framework of our conference, and I hope the result of your work that will be present in this conference would be published in the high level rated journal. Also, I would like to wish everyone success. I wish everyone good health, and our coming them in the strange in our coming the discovery that you among all Ukrainian people face in these hard difficult times. Thank you. And now let me start our symposium, the law of dimensional and nanomaterials. And with great pleasure, we will take this microphone to our case speaker, Professor Valery Skrishevsky from Institute of High Technology, Tarasa Shevchenko National University of Ukraine, Kyiv. Please, Professor Skrishevsky, please. We have your microphone. Okay.
Okay, thank you very much. Dear colleague, hello everybody. I would like to say a lot of thanks to organize of this very nice conference, because really it's very important event for Ukrainian today. We would like to obtain new information, new contact with colleagues from Ukraine and from other countries. I hope that will be useful for submit new mutual projects and continue working in scientific field, not only high technology, but other one too. So my presentation concerns synthesis and application of carbon-based nanohybrids. And you can look team that was presented, Leon University, Claude Bernard, Kyiv Taras Shevchenko University, with collaboration with Science Park of Kyiv University. Okay. Sorry. Okay, today nanoparticles is very famous subject for investigation and for practical implementation, but a lot of material related to quantum dots. I will say only about carbon dots, and there you can give definition what is the materials. Carbon dots are zero-dimensional carbon-based nanomaterials that consist of dense core formed from stacked multiple graphene fragments in ordered or disordered, and functionalization by different species. You can see. So, for example, graphene quantum dots, carbon quantum dots, carbon nanodots, carbonized polymer dots, etc. There are a lot of methods for synthesis. Only briefly: chemical oxidation, laser ablation, RD charge, electrochemical methods. Bottom-up approaches consist from hydrothermal, microwave assist method, pyrolysis. Mutual for this method is necessary to take some carbon-containing materials and using different procedure, usually thermal or another one, in order to obtain carbonized processes. You can look, for example, next one. For example, few processes, synthesis of water-soluble carbon dots from watermelon peel, from lychee seed, peanut shell, and other biological materials. In our laboratory, we elaborate some procedure to prepare carbon dots, and it's usually more general, and can explain using this picture. You can see, firstly, we take some urea or citric acid, added salt of gadolinium, and after that, add this mixture to glass reactor, placing in oven with temperature 135. After that, increasing the temperature, preparation of solid materials, cooling, adding water, gommonization, filtration, centrifugation, obtain very small particles. Typical dimension a few nanometers, from 2 up to 10 nanometers. And another one, for example, we use different organic waste like this one, coffee-based materials from waste of after eating of coffee. We use these materials for preparation nanodots. So you can see it's a very interesting subject, because there are a lot of materials that can be applied for preparation and synthesis of such materials. They may be biomolecules, proteins, amino acids, carbohydrates, medical plants, fruit, roots, stems, etc. So such materials give very interesting properties. This is presented tree that explain what the main advantages of such materials: high quantum yield, upconversion fluorescence, good photocatalyst properties, high photostability, water soluble, chemical inertness, facile surface functionalization, easy synthesis, no toxic, solar energy conversion, wider photo absorption. So it means it's very simple to prepare such materials, and there are a lot of perspective for practical application. And the first of them is necessary note that very high efficiency of luminescence. And such materials can be obtained up to 100% of quantum yield for luminescence. And this spectra is very complicated because luminescence consists from different parts. One of them from carbon core, another one from surface states. And you can see this picture that explain the transmission between homo-lumen transfers of energy with luminescence in core and in surface state. Using these materials, we can obtain different luminescence spectra, and some of them will be excitation dependent, another one will be excitation independent. Change the structure of core, we can obtain blue luminescence, violet, green, yellow, and another one from surface state, we can obtain another spectra of luminescence. And since these materials complicated in structure and some of luminescence depend on surface, this fluorescence will be depends of solar polarity and structure of core. And so just I will be present where we can use such materials. Firstly, fingerprint identification and anti-counterfeiting badge, because strong luminescence provide very useful information about fingerprint. On the left side, you can see badge is different color of letters because under the different excitation, we can obtain luminescence from different letter. Another one, it seems to me more important, is application for biomedical. And you can see in vivo imaging and in vitro and ex vivo imaging. And after injection, intravenous injection of carbon dots, you can see luminescence from thoracic region, area of liver, small intestine, large intestine, bladder region in different time, because nanoparticles will be released during a few hours. And you can see that more intense luminescence from liver, bladder, and lung. There are very important properties that we can prepare complicated structure that consists not only from fragment of carbon, but in different metal. Especially it's important if we add some gadolinium-based materials, because it's nice contrast, and such materials is paramagnetic. It's toxic materials, but in the complex of carbon dots, it provides some behavior like paramagnetic center, but not toxic for living cells. And you can see it's multimodal application. From left side, you can see luminescence for imaging. From right side, you can see relaxation time of particles that compare with water. So multimodal application, it's important for biology, but not only, because today there are few work devoted to application for therapy. For example, some of work gives information that during the illumination of carbon dots, it's possible to generate reactive oxygen species. This species can produce damage of DNA up to necrosis, apoptosis, because it's very important direction in therapy. Another one is accident activity, because can be produced under illumination RNS. This is a reactive nitrogen species that has some cytoprotective effects. And this is explained what is different between photodynamic therapy, when under illumination we can obtain reactive oxygen species, or effect photothermal therapy that is important for local heating. And during the local heating, we can produce local increasing of temperature that can lead to apoptosis or necrosis, depends on temperature. And we have some project, and one of them is UNAT project, a frame of Horizon 2020, and use so-called photoacoustic therapy. When in mouse we inject carcinoma laevis lung and inject nanoparticles and illuminate from pulse lasers. And you can see the effect of therapeutic related to photoacoustically induced destruction of cancer cells. And you can see surveillance increase up to 30%, and local temperature increase only a few degrees. It's not photothermy, it means photoacoustically induced. A lot of work is devoted to application like sensor. For example, on the left side, you can see impact of pH from acid to alkali, and you can see a very strong change in luminescence mapping. Exactly from right side, is curiosity, we apply some liquids, for example, alcohol, cognac, whiskey, etc. There are some very nice distinguish of these liquids by luminescence mapping. But more important, it seems to me, it's measure ions of heavy metals. It's very simple procedure. If you select some particles that can be provide very strong luminescence, and surface will be activated some species, for example, carboxyl groups or amino, and after preparation such nanoparticles, carbon dots, and adding ions of ferrum, luminescence strongly decreases because it's effect of quenching. And you can see that the effect is selective. Only ferrum ion is active, another one is not gives such effect because it depends of surface passivation such materials. More complicated, but more perspective using mechanism on-off-on, adding during illumination the luminescence, adding nanoparticles, luminescence quenched, and adding lysine, luminescence recover. Such a sensor has high sensitivity, high practically, because can be applied for different kinds of water, and fluorescence totally recovery. Today, start new approaches for apply so-called FRET effect. FRET effect is effect of resonance energy transfer. It's necessary use two kinds of particles. First one is a donor of carbon dots with very strong fluorescence, and absorbance careful acceptor, for example, dye, rhodamine B or another one. If luminescence or fluorescence of nanoparticles, carbon dots, overlapping absorption spectra of donor, there are some process transfer energy from donor to acceptor, and in the presence of metal ions, FRET process will be blocked, luminescence strongly decreases, and can be used some obtain some nice law of detection, only ppms. It means very sensitive approaches to obtain very sensitive sensors. In Ukrainian conditions, may be interesting application using sensing for the need to low, toluene or another one explosive materials, because luminescence can be quenched in presence such explosive materials. The main explanation why this effect is has specificity, especially for concrete types of explosive materials, is explained by this model. For transfer energy is necessary that level of luma explosive material will lower the luma of carbon dots. Only in this case we can obtain quenching for such materials. For another one, it will be not work. Another part of my presentation devoted to energy. Here is a timeline of solar energy conversion efficiency research from last 50 years according to National Renewable Energy Laboratory. You can see that efficiency of solar cells, blue line, is silicon one. And today is more important material for solar cells batteries. There are other approaches to increase efficiency, but its materials will be expensive. Another one, materials more cheaper, but has lower efficiency because necessary coincide this triangle of we would like to obtain such materials with long lifetime, high efficiency, and low cost. Today, practically industry selects silicon, but silicon is not optimal for this purpose. And some of scientists and technology look possibility to increase efficiency of silicon solar cells. More simply, to add some luminescence quantum dots on the surface silicon solar cells and use an effect of down conversion. So absorption in ultraviolet and emissions of quantum dots in visible regions that more compatible with solar cells based on silicon. But unfortunately, effect is very small because ultraviolet is a very small part of solar illumination of the surface. So more perspective using down conversion that ultraviolet will be absorbed on carbon dots and generate two visible photons, like on the right side of this picture. So the main requirement is necessary use quantum dots with very high efficiency and quantum efficiency of luminescence. And exactly, there are some fast works devoted that really it's possible to obtain such effect using the polyvinyl pyrrolidone with carbon dots, such matrix with this polymer and graphene carbon dots. And you can see that there's very small effect, but anyway, 2% in absolute increasing, it's important result. This is sorry. Так, 5 minutes. I would like to say the last part of my presentation about energy storage. This is a region plot for several types of electrochemical energy storage. You can see that fuel cell has very large energy density, watt hour per kilogram, but power density watt per kilogram is small. Supercondensator capacitor has power density large, but small energy density. And so battery lithium in the middle between fuel cells and supercapacitor. And last year, RISE was published a few work devoted what we can use for such energy storage using the carbon dots. First one, apply for lithium-ion batteries, because today disadvantage of lithium battery is high cost, toxic electrode materials, and operation safety problems. And the main goal aim is reduce cost using non-toxic materials for electrode, increase number of discharge charge cycle, it replace lithium with sodium ion, and reduce impact of aging. And the first work devoted to such approaches use some nanobelt array when carbon dots will coat it on vanadium oxide. For example, for this is parameters, you can see that cycling performance is not so bad because it's stable result. For another application, for fuel cells, again, fuel cells used for lithium proton exchange membrane. Sorry, it's proton exchange membrane application for hydrogen energy. We add to PEM fuel cell hydrogen, oxygen from atmosphere, and obtain electricity and water like this. But unfortunately, this PEM fuel cells has high cost, low durability, and the cathode operated 6 order of magnitude slower than anodic hydrogen oxidation reaction, and thus limit performance. So idea is use replace some platinum electrodes for more cheaper materials. For example, we consider possibility to add some mixture between or hybrids of carbon quantum dots and black platinum. And for supercapacitor, the same, there's some approaches, preparation electrodes from using of carbon dots. Only few work I find in literature, and anyway, some scientists look that it's possible to change some electrodes for more cheaper from materials using carbon dots. And the last, photocatalytic. Photocatalytic, it's important part because we can produce a hydrogen from water, but today photocatalysts use materials that has not optimal band gap. Usually band gap is very large, and such materials very badly absorb visible light. It's necessary to use ultraviolet. Ultraviolet, it's very small part of solar spectrum. So idea, the working principle is light radiation of a catalyst, put excited electron, reduce protons in solution to hydrogen atoms that hemisorbed on the surface of a catalyst, which are then desorbed as a molecule of hydrogen. But if we add some small carbon dots like this one and use effect of like FRET, resonance transfer energy, and it can provide for us new possibility because the surface will be strongly increases, specific surface. Secondly, band gap will be more optimized for solar spectrum, and such materials can improve efficiency of catalyst such materials. Here, models that explain what is happen. But if you look on the right side, you can see that really absorption increases. So efficiencies such materials like catalyst is better. Secondly, model explain why it's happened due to illumination. It's very simple, like solar cells, because there's some p-n junction, and they improve efficiency of catalyst. On the right side, you can see the emission of hydrogen due to elimination of such materials. And the last mechanism for the catalyst, for example, if we use typical platinum, add some carbon dots and hybrid platinum carbon dots, effect of transfer energy, provide generation of hydrogen and water. So this briefly my presentation. Like summary, I'd like to say today carbon dots is practically new materials. They applied for various application, diagnostic and therapy, energy storage, solar cells, catalyst, and other ones. This is a picture that show perspective application. But main problem that today mainly only idea or laboratory stage, not verification and proven in industry. And today it seems to me it's perspective direction for submission a new project, because Europe and other country look new materials for lowering carbon dioxide lowering emission to improve efficiency of different energy sources, like yesterday say about this situation and economy and real politics. Andrei Ragula, in his speech, he say about main perspective scientific research in Europe and the world. So I would like to say many thanks for my colleague from Kyiv University, Institute of Palladia, University of Haute-Bernin, France, and this work was supported by Horizon 2020, Maria Skłodowska-Curie. Thank you very much.
Thank you very much for your very interesting and valuable talk. And I have some questions about your work. First of them is, what is the mechanism, physical chemical mechanism of the fixation photoluminophore part on the surface of the quantum dot, quantum dot particles?
Usually, main mechanism that more general is exciton luminescence, because nanoparticle is not solid materials, is more closely to polymers and molecules, so they are separate levels, and exciton luminescence is more preferable mechanism. But some of them, if particles very large, the core consists from dense materials, so it's necessary to apply model band gap like in solid state. So it depends of what kinds of materials we
Okay, but I ask about photoluminophore part. What chemical mechanism of the fix the photoluminophore? Maybe it's reactions on.
Yeah, fixed some of them. Just I say about a colloid solution. This colloid solution can be added in matrix of porous matrix. Or prepare a mixture of polymer and colloid particles. One of the properties of such materials is very strong luminescence when particles separately each others. When we coincide together, prepare like powder, luminescence strongly reduced. Yes. So it's necessary to separate these particles to improve the efficiency.
Luminescence depends on the concentration of luminophore.
The size depends effect of luminescence. Yes. Is very strong.
Yes. I know. Another questions correspond, how do you use your quantum dot particles in photodynamic therapy? How does it work?
Thank you. Thank you for your question. Really, it's very important. There are some models. One of the model is nanoparticles absorb light and generate reactive oxygen species. Of course, it depends. It's necessary same additional materials, so-called photosensibilizer. So particles can be act like photosensibilizer, or maybe can work together with another one. So it's not simple for explanation such mechanism, but really it's work. And when we as say our classic, this is work in the future.
Okay,
This problem. For me, it's not simple to explain what is happening with biology.
Yes, I understand, but it is very interesting. And do you tell about the catalytic or photocatalytic process? Because it is
I say about
photocatalytic influence the light, but catalysis is temperature. But you tell about catalyst or photocatalytic activity of the quantum dot particles.
Here I say about photocatalytic.
Photocatalytic under visible light
Yeah,
condition.
visible ultraviolet, because we can tuning band gap, not band gap, levels, energy levels of particles, especially for spectra, because due to synthesis, different mechanisms of synthesis, we can obtain particles very large, very small. For large particles, not interesting like photocatalysis, only interested for small one.
I understand, but what's the value of the band gap energy of the carbon? I really don't understand the.
It depends on size, but
carbon shows the band gap energy. I see.
For particles, we cannot say about.
Not semiconductor, but
yes,
it's
not
isolator
not
maybe.
metal. No, it's more closely to dielectric. Isolator.
Directly, how does it work with band gap energy? And I really.
But we didn't work with
okay,
solid bulk materials. We work only very small one.
Very, very interesting. Okay, thank you very much for your questions. Ask any questions in the hall? No. Yes? Okay.
I have only small remark because it's really interesting approach from agriculture waste to the solar cells and so on and so on. So from fundamental to the high technology. So it's very interesting approach. Thank you very much.
In my speech, I'd like to explain general.
I am not specialized in nanomaterials, but it was really insightful speech.
In agriculture, yes. But I would like to say that for these materials, we can use different materials for preparation carbon dot.
Thank you very much for the report. Very impressive directions where the carbon dots, as you call them, can be applied. I have two small questions. Why carbon and not quantum dots? What's the difference? And another one, I will ask them, I'll fire away. You said that industrial implementation isn't sufficient, let's say. Why? What are the reasons? So the first one is why carbon dots instead of quantum, and the other is industrial.
Quantum dots only this, we say when we have luminescence that can be explained by the exciton. But general carbon dots may be quantum dots, maybe not. It depends on size. If size 10 or bigger nanometers, it's not quantum dots. It's carbon dots, but not quantum. But if size
So
less.
it's a highly dispersed particle of carbon.
Yeah.
Okay, okay.
For implementation, it's a complicated question. Exactly, I see it on the nearest future. We will be more detailed about how to use it in concrete industry or concrete therapy, because not so simple. All work that we can look in literature, it's especially research. But how it's coincide with industry, for example, if we say solar cells, it's not technology, spin coating or sputtering particles on the surface of silicon. It will be not stable under outdoor conditions.
Okay.
But in laboratory, it's okay. Efficiency increase, particles work like supplementary for improve efficiency, solar cell.
So the
but
problem
not
is the
but not
stability
for outdoor.
Is the stability of the overlay.
Stability, aging, important problem. So for industry, it's necessary add such particles to matrix and prevent interaction with air,
With the elements, yeah, I see what you mean.
water, etc.
Thank you, thank you.
Okay, other
Thank you.
questions online? No questions online? Okay, we will thank our speaker again. And thank you very much for
Thank
your
you.
previous
Thank you.
talk and diploma. Maybe
Oh, yeah, diploma.
where is diploma?
Thank you for diploma.
Oh, okay. Okay.
Oh, thank you, sorry.
Oh,
Yeah, well, thank you.
okay, and one photo. Okay, okay, it will show. Okay, okay. We will go there because on the screen. Okay, okay. Okay, okay. Okay. Okay, okay. 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 You get that. Okay, then thank you again. Okay, and our next speaker will be Mark Apilevich from the LCT, yes? Research Gesellschaft mit geschränkte Bedarf. And from Österreich, yes, yes, research center, yes. Okay, Marco, are you here?
Yes, you can hear me well?
Okay, please share the screen, please,
I
and
think I did.
we are ready to listen to you.
Can you see my screen?
Okay. Yes, okay, okay,
Okay.
everything is okay, yes.
Okay, thank you. Okay,
Thank you.
I would like firstly to thank to organizers for inviting me, especially to Marina Storozhenko. Really nice to be invited here to this wonderful conference. My name is Marko Piljević and I am PhD student in second year at Technical University of Vienna. And I'm doing my project on green synthesis of MXenes and potential use as a solid lubrication in two companies. One is AC2T Research, as you said already, and the second one is CEST, which is Electrochemical Center in Wiener Neustadt, also as a AC2T, and in collaboration with Carbon Ukraine, who provided us really nice, high-quality MAX phases. So I will first start with MXenes. You already had opportunity to hear yesterday Professor Yuri Gogotsi, but I will just use one slide for this. So MXenes are 2D materials compounds which are discovered 2011 at Drexel University, and they're formed from MAX phase. So MAX phase is a precursor from it. MAX phase is built up from three different elements. First M elements is usually some transitional metal. Then we have most typically aluminum here, and or other these blue elements can also be there. And for the third one is usually carbon, but we have also nitrides, carbonitrides, and also some forms of oxygen sometimes. So the idea is that HF acid is used for aluminum etching. So I will show now on this example here, which is most famous one. So aluminum is etched with HF acid, and then we have this titanium carbide formation, which is MXene, and we have also a new element, which is surface terminations, which is mostly some oxygen or fluorine atoms on the surface of this layered structure. So we will see here one typical picture of SEM picture of MXenes. It's layer structure, that's why it's 2D material, and that's why it's called actually MXene, to remind us of graphene. So it possesses similar structure, but it's more complicated a bit. So it is already known that MXenes are really powerful materials. They are used in many different possible investigations, from energy storage to water purification, optoelectronics, sensoric, biomedicine, also in tribology you will see today. So really powerful, really versatile material, and it can be in theory used in future in many applications. So I will start with the problematic of some of the procedure which is used for the synthesis. Most typical synthesis is including this HF acid, hydrofluoric acid, which is highly toxic acid, and it can penetrate easily to the skin, to the nerves, and it can damage easily the health. And you can see here that if body gets exposed 2.5% approximately, it can be also fatal. So here are also some effects shown that if you are working with, it's really, you need to be really careful when you work it. And also, no, it's not about that is just dangerous. There are also many strict regulations, especially in the European Union, also in the rest of the world, that you need to accomplish before you start working with HF. I also heard that before you start working with HF, you should also contact local hospital before you start working with it. So it's not a joke, it's really nasty chemical. And there are already other synthesis methods which are investigated in the literature. And you can see here, people are trying to replace mostly with this mild method, where we have two fluorinated, so we have salt, fluorinated salt, and HCl in situ to produce HF. But there are also other ones like electrochemical etching, molten salt etching, hydrothermal, and many other ones which I didn't mention. So I will focus today on my approach, which is, or I would say our approach, which is electrochemical etching. And I will start with the procedure, how we started and developed this, the method actually. So we used 3 electrode system for this electrochemical etching, where we put as a working electrode, you can see it here, we put this max pellet. So we attach exactly on the clamp as a working electrode, as an anode. Then we have carbon beaker, which was in our case counter electrode, and the platinum electrode was placed in between 2 track potential. You can see also here schematic of the same of the same cell actually. The idea was to have this max pellet here and to etch MXenes with some electrolyte. I will speak about that later. And the MXenes will then fall down in the solution and being collected in carbon cup. So this work is already published in this year in small journal. You can scan the QR code here to find more info. As I said, firstly, we needed this setup, which is 3 electrode system to do electrochemical etching. More info about that on the next slide, which electrolyte we used. The second step was, which is also important, was to destroy these layers between the etched MXenes, to destroy these van der Waals interactions, to make them weaker, so you can also spread the layers and then exfoliate MXenes. So we did this with DMSO because it's a nice molecule to intercalate between the layers. And the last step was done in water with ultrasonication. We destroyed completely van der Waals interactions, and we got few layered MXenes as a final product. So you can see here that in completely procedure, we didn't use any toxic material, which is also a novelty in the literature. So how we started actually, what we used as electrolyte, first we needed to screen some possible electrolytes. We did cyclic voltammetry tests. So it's actually scanning potential and tracking the current density. We started with HCl acid, and you can see here that we did this cycling like 5 times, but there was no clear peak in this voltage region. Then we did the same procedure with ammonium fluoride. There was some peak, but you can see that after each cycle, peak was shifted, so it was not quite stable potential. And also, you can see that current density is quite low because we multiply these results by 5 so we can compare the results. And the last one was actually the best one for us. This is a mixture which contains sodium tetrafluoroborate, HCl, and DMSO. And you can see here that we have multiple peaks, but first one at 0.65 volts was actually etching aluminum peak for us. So when we applied voltage at this point, we were etching aluminum from max phases, and then we got MAXenes. We also tried to investigate these other peaks, and we got that they are over-etching peaks. So we got some titanium dioxide formation on the surface of the pellet. So it was too harsh for this etching potential. So the next problem was, okay, we know what is potential to etch MAXenes, but as we also know that max pellet was hanging in a solution, it was producing MAXenes, but on the surface. So we needed somehow to clean the max pellet to reactivate electrochemical activity of the max pellet electrode. So we didn't want to apply any mechanical force because it can also disrupt MAXenes, also like ultrasonication, it can heat. So what we actually decided to do, we did after each 1 hour, we applied strong negative pulse in voltage of -1 to produce hydrogen on working electrode. And you will see that after each 1 hour, we got strong current after each application of these strong pulses. What was the goal actually? That we produce hydrogen on the max pellet, which bubbles will burst, and then it will clean and reactivate electrode. So after each 1 hour, we did this reactivating of the electrode, but after, let's say, 2-3 days, it was dropping in the current density, and we reached quite a low current. So there is still place to improve this method. So typical synthesis procedure, as I already said, first we have max pellet. You can see here how it looks like in the SEM, so quite stiff material. You can see it also here. This was actually our working electrode. Then we had we done this etching with electrolyte and voltage, and we got this multi-layer MAXenes. Now you can see exactly how it looks like actually like a book with many pages. So the next step would be to destroy these van der Waals interactions between the layers and to get to few layered MAXenes. And you can see how it looked like after 2 days etching at room temperature. We got this black powder of electrochemically etched MAXenes. Then we did a lot of different characterizations. I will show only a few of them. So we did SEM, we did TEM to prove this layer structure. We also did AFM to investigate how each flakes look like. And we could see that flakes have this curled structure, most likely due to hydrogen bonding formation in surface terminations region. We also did XRD, we did Raman, and we could see that with this method, we are getting mostly few layered MAXenes, so nicely dispersed MAXenes after the synthesis. And what is also interesting with this method, on the surface of MAXenes, we got mostly oxygen. So in our surface termination, we mostly have this OH, so hydroxyl groups or double bonded O, and only few fluorine. But in HF MAXene, we have mostly fluorine, or let's say half of that was fluorine terminations. Why is that important? Because the properties of MAXenes are depending on these exactly terminations. Why is good to have oxygen termination? Because they are tunable. You can attach whatever you want to this OH group, what is reacting actually with hydroxyl group in general. So you can attach and then tune MAXenes to different possible properties, let's say, to achieve some different properties. So we can say they are tunable in the chemical way. This is also a nice method, which is first time ever done on MAXenes. This is low energy ion scattering, or LICE method, which is using low energy noble gas, most likely helium or neon. and they scatter on the surface of some material, and it can measure directly first atomic layer. So it will not penetrate through the layers, it will measure exactly first layer, and that's why it's really superior. We also try to measure on our MXenes, and you can see here that, for example, when we compare it with HF, you can see that we have mostly O terminations comparing to F, which is lower intensity. In HF, it is opposite. So it's still not possible to quantify it with these methods. With XPS is a bit better, but with LICE, there are still not standards. But for qualitative analysis, it's really superior investigation method. So now when we know that MXenes already possess some nice properties like friction reduction, tribophile formation, or low shear resistance, so they can slide, these flakes can slide over each other, can we maybe say that MXenes are emerging as a promising solid lubricants? Why solid lubricants? Why we need solid lubrication? For example, in vacuum or in space, it will be hard actually to lubricate machine with oil or grease. So we need something that will be stable under the vacuum in high temperature, so that will also reduce friction and wear. And MXenes are emerging as a promising material for that. Also, you can also apply this powder in nanoscale applicability, like in some chips for some also solid lubrication. Here you can see that when they are invented let's say this year, MXenes publications are really raising. Let's say per year we have now around 50,000 publications. You can see here that also MXene in tribology is really increasing topic. So I see really bright future for these materials in solid lubrication. So yeah, as I said, this project was developing a green method for synthesis, but also testing in solid lubrication. We did some coating preparation. You can see here how easy it is to disperse these materials. We did this in ethanol with 2 milligrams per milliliter. We dispersed it with this tip sonicator. You can use also ultrasonic bath. And then we just spray it with air gun, which is like 20 euros. So it's a cheap method, but it's giving really nice coating. You can see it here. This is like with 2 milligrams of MXenes. So it's covering really huge surface area. Then we did really, we wanted to test this in solid lubrication. We did one linear reciprocating test where you have like a ball over the steel disc, which is just going back and forth and measure coefficient of friction. We did this with 3 different counterbodies. First, we investigated silicon nitride counterbody, because this is actually first time that someone measured solid lubrication of O-terminated MXenes, because usually people are working with this F-terminated or something in between, but this is first time that we actually tried it, and we wanted to see, okay, what is working the best. Silicon nitride, you can see coefficient of friction was around 0.2. Which is quite low, and it was stable in this case, and comparable to the coefficient of friction when there was no MXenes, it's way better. So it's reduced for 3 times, and it was stable after 15 minutes with silicon nitride ball. But when we tested with alumina and with steel, it was giving a bit worse results. With alumina, after 5 minutes, the tribofilm formation was almost gone. So you can see here that the coefficient of friction was raising after 5 minutes, and with steel it was even worse. We then wanted to investigate which mechanism is actually lying behind this. Eduardo Marquis from Technical University of Vienna did nice DFT calculations and proved that adhesion energy is highest for these MXenes in the case of silicon nitride. And this just confirmed our best results in solid lubrication. So we did many different characterizations. You can find this still as a preprint online. So I hope that in near future it will be published somewhere, because it's really nice paper. You will find it, you can scan it and find it, or just search it and you will find it online. So to conclude, these steps we did in our approach. So in 1.5 years, we found this nice etching method. We can also use powder as a starting material, but in this case I showed you pellet. Then we got this electrochemical etch MXenes, which were sprayed and then tested in tribo tests. So we can say that this is completely green production with no toxic material. It has, of course, upscalable potential and huge functionalization potential due to surface terminations, which I already said are oxygen, and they're wear resistant. So at the end, I want to thank to Land of Lower Austria, which funded this project, and I want to thank also to my collaborators, which are shown here, and also people who are not shown here but were included in some point in the research. And I want to thank also to my company ACT2T Research and CEST for collaboration, and also, of course, Technical University of Vienna and Carbon Ukraine for providing high quality material. So if you have any questions, you can contact me over this email, or you can ask me now as you prefer. Yeah, that's it from my side.
Okay, thank you very much for very interesting talk. And really, MXene material-based materials are very interesting. And I have two small questions. First of them, could you tell about the general specificity and properties of the MXene type materials? And the second one, the question is now the materials based on MXene used in the practice, or it's planned to use in the future? Thank you.
Yeah, no problem. I will start from the second question. As I know, they are not used still industrial, so they have still some issues like oxidation stability. They are prone to oxidize during time to produce like titanium oxide if we speak about titanium-based MXenes. But I see bright future if we compare it, for example, with graphene or with some other 2D materials. We have really bright future in terms of that we can make different, unlimited actually, different compounds. So whatever we want to achieve, we can modify or synthesize during the process. So due to different kind of metals, different kind of surface terminations, we can achieve different properties. When we speak about what was first question was about the properties itself. So it contains properties from the metal because it has like one layer metal, one layer, I would say graphene, one layer metal. So it's a mixture of metal properties and graphene properties. So it's a high conductive material, also mechanically strong material, if I can say it like that. And if I say in general, I would make a mistake because each of these MXenes has individual properties. So I would say they are really nice materials to work with, and I see a future with them in many different fields.
Okay, thank you very much. And other questions? Okay, we see the questions in the poll.
I have some small questions. First of all, what was the size of the powder you obtained? And what's the method of coating spraying did you use? Because as I know, not all methods are available to spray coatings with MXenes because, for example, plasma spraying is not available because the MXenes are destroyed in the process due to high temperatures and so on.
Yeah, okay. Yeah, the problem with MXenes, if you hit them in some media, they will oxidize. So you need to apply them in some mild application method. In this case, we just disperse them in ethanol. You can also use some other solution like acetone. But for me, ethanol was always working well, so I was not investigating other ones. But I saw in literature. And this setup really costs like 20 euros because we bought this over, I will not put advertisement now, but you can buy it online for 20 euros and you can just apply it to some air pump and spray it. So you will use this dispersion, put here 2 milliliter and spray it with air and you will get a really nice coating. You asked me about the size. Coating achieved with this was in the range of 0.5 to 1 micron. but it's hard to measure exactly because you saw the flakes are curled, so it's not forming one exactly coating on the same level, but you will have, bigger and higher and lower parts of the coating. But in general, it's really consistent. You can see that with 2 milligram per milliliter, as I remember, I sprayed here like 2 milliliter only, and you can see that half of it went out of the zone where I sprayed, and maybe I would say maybe even 1/3 went on the disc, and you can see how consistent this coating is. So it's really nicely dispersible in ethanol, also in water, but ethanol I use because I sprayed it to easy evaporate, of course, ethanol, to avoid droplets. So the disc was preheated at 100 degrees, and then it was just sprayed in like 20 seconds. So it's quite fast and quite good method to apply them.
Okay. Thank you very much for your answer. We will
no problem.
send
May I have a follow-up? So after applying it like that from the ethanol solution, what do you do? How do you make it stick to the surface?
So after applying in ethanol solution, we were using, so here I have photo with tip sonicator, but most likely I was using ultrasonic bath. So like 30 minutes, or I don't remember exactly for this one, maybe 1 hour at room temperatures, just sonicating to spread, to destroy the interbonding between the layers, because when they solidify after the synthesis, they're really solid. So you need to somehow destroy them, spread the layers, destroy the hydrogen bonding, and this is done exactly at room temperature, just with ultrasonication waves. After 1 hour, it was stable dispersion, and then we just applied it, and that's it. After that, it was stored in vacuum and used.
Thank you for extended explanation. That's how you produce the colloid. Yeah, the paste you spray. No,
Yep.
not the paste, the liquid you spray. But I mean, after the deposition, this is just a layer of non-bonded coating on some kind of substrate.
Yeah, this is exactly, this is metal.
Is this a target, or should we maybe want it to stick very well for the particular application we want to use it in?
Yeah.
Am I clear with what I want to ask? Yeah.
Yes, of course, because
I mean the adhesion to the adhesion of the final coating to the article we are producing, to the coated article.
Yes, yeah. In this case, we use steel as a substrate. So steel, as you know, it also has on a surface oxides, or maybe also hydroxyl groups, and it can bound with the MXenes, which also have these similar groups. It can bound hydrogen bonding, and that's why we have this stable coating. So you can apply to also different kind of materials. In this case, we just use the steel because we wanted to investigate tribological properties of the steel versus different counterbodies. But you can try with different. I also did it on aluminum. Yeah, I didn't investigate too much different. Yeah, aluminum was the second one I tried. It was also stable. It's still stable. I have it like after 1 year coating is untouched.
Okay, thank you.
Yeah, you're welcome.
Okay. Other questions online? No questions? Okay. Hence, we will thank our speaker again. And thank you very much. And our next speaker, Anatoly Lemish from Francevich Institute for Problems of Material Science. Anatoly here or online?
Yes, I'm here. Oh, I'm online.
Okay. Share please your screen.
Okay, I will share the presentation. So
presentation.
I'm gonna share it.
No, okay, full screen.
Do you see it?
No, we see, but not full screen. Oh, okay.
Okay.
Okay. Yes. Okay. No, it was better before.
Was
Before,
was better
yes.
before?
No, not full screen.
Not full screen. Okay, so like that.
Yes. No, 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 no.
I don't really understand what you mean, like not full screen. So, is it okay like
Oh,
that?
okay, okay, okay. We will see all your presentation. Okay, please.
Okay. So, good day, everyone. My name is Anatoly Lamish. I'm from Francevich Institute for Problems of Material Science and from KPI's Faculty of Electronics. I will talk about the effect of cadmium doping on zinc oxide microstructures grown by the atmospheric pressure metal-organic chemical vapor deposition. So to start with, zinc oxide is a transparent wide bandgap semiconductor material which is widely used in the optoelectronics, photovoltaics, and nanoelectronics. And doping it with cadmium, which is an isovalent dopant for this material, narrows its bandgap, which changes its properties and is great for the bandgap engineering and changing the photocatalytic properties of the material. For the purposes of this research, a high specific surface area was required, which is the reason we use the APMO-CVD for synthesis. So to determine the effect of the atmospheric pressure MOCVD on the zinc oxide cadmium microstructures, we synthesized the sample of the pure zinc oxide and zinc oxide doped with cadmium, different samples, and investigated their structure and properties. So the samples were obtained from the mixture of precursors of the cadmium acetylacetonate and zinc acetylacetonate of high purity over 99% each, with the concentration ratio as shown in the table on the slide. So the pure zinc oxide and then the mixture of precursors with different weight percents of the acetylacetonates. They were placed in the ceramic plug into the tubular electric furnace, which is divided into different sections, heated to different temperatures for the precursors to evaporate and then to deposit on the silicon substrate. So then the obtained samples were analyzed and researched using different analysis methods described here. So the scanning electron microscopy, X-ray diffraction, energy dispersive microscopy, Raman analysis, photoluminescence analysis, and photocatalytic activity analysis using the equipment shown on the slide. The first result was of the scanning electron microscopy, which shows the morphology of the samples, and they appear to be the branch-like agglomerations built from nanospheres of the material, and with high concentrations of cadmium acetylacetonate in the mixture of precursors, the structures become less evenly spread across the surface of the substrate. However, the energy dispersive spectroscopy shows that zinc and oxygen are distributed almost evenly in the places of the microstructures on the silicon substrate, which indicates that the material obtained is really zinc oxide. And it might be seen that also on some samples there is a formation of the thin film of zinc oxide on the silicon substrate. However, as you can see from the concentration and from the pictures of distribution, there was no cadmium detected using EDS. It is also seen the visibility, change in visibility of the silicon substrate of different doped samples is determined by is dependent on the distribution of the microstructures across the surface, but you can see that there is more zinc than oxygen in almost all the doped samples, which might be an indicator for inclusion of some of the cadmium ions in the sublattice. But further analysis showed that the cadmium is included, however, was not detected by the energy dispersive spectroscopy. So firstly, for X-ray diffraction, it shows that the material has a Versed type structure, which is typical for zinc oxide. And the shift of the peaks with high cadmium acetylacetate concentrations in the mixture of precursors show that there is some deterioration of the crystal lattice, which might indicate on the inclusion of cadmium ions. And we also calculated the grain size of the crystal lattice of the samples using the Biesheurer formula. And it is shown that for samples with 5 and 7.58% of cadmium acetylacetate, the grain size is bigger, which also has the effects on the latter results of analysis. So Raman spectroscopy, the spectra demonstrate modes at 99 centimeters to -1 and at 437 centimeters to -1. E2 low and E2 high, which are the allowed modes for zinc oxide. And E2 high mode position is yet another indicator of the of the cadmium inclusion in the material. As for the pure zinc oxide, the peak was located at around 437 centimeters to -1 and had 0 residual stress, which was calculated by this formula. But with the inclusion of cadmium acetylacetate in the mixture of precursors, the peak shifted to around 435.5. And the residual stress in the material became evident. Also, the peak A1 low shows indicates the deterioration of the crystal quality of the material. The spectrum of photoluminescence shown here has 4 peaks at near band emission in the ultraviolet region, the peaks in the blue region, yellow, and in the near infrared region. So NBE, near band emission of energy, at first, with the inclusion of cadmium acetylacetate, the intensity of it increases, then drops at 5.8%, and then the peaks smear and shift for the samples with 7.5 and 10.8%, and they shift to the violet region. It also indicates the decrease in the band gap and the appearance of the number of energy levels in the forbidden band below the conduction band, which is which also might be due to the deterioration of the crystal quality. The peaks in the blue region became evident only for samples doped with cadmium, and usually the blue emission can be related to the transitions involving zinc interstitials or zinc vacancies. However, in our case, the pure zinc oxide sample didn't have that emission, so it indicates that cadmium ions are predominantly responsible for this type of emission. For the emission in the near infrared region, as it follows the similar pattern with firstly increase in the intensity, then decrease at 5.8%, and then the shift of the peaks. It is the second order diffraction of the NB in the ultraviolet. We calculated also the contribution of the violet band, blue band, and yellow bands into the photoluminescence, and the blue band has the increased contribution for the samples with 1, 2.5, and 5.8%. But then this contribution drops with the higher rates of the cadmium acetylacetate in the mixture of precursors. Yellow band and violet band follow the same behavior for all the samples. So lastly, the photocatalytic activity of the materials were investigated using the methyl orange as the model pollutant, and it has 2 peaks on different wavelengths, at which photo degradation can be monitored. We have chosen the peak at 465 nanometers to monitor it. So we made the solutions with MO and then placed the samples of the pure zinc oxide and the cadmium doped zinc oxide microstructures into the solution and irradiated it with the ultraviolet mercury lamp for 3 hours. And notice the results at 1 hour, 2 hours, and 3 hours, respectively, which might be seen here. So here is shown the concentration of the methyl orange during that irradiation time. And we can see that for pure zinc oxide, the difference in the concentration is not that different from the natural photodegradation of methyl orange under ultraviolet light. But with the addition of even 1 weight percent of cadmium acetylcysteine to the mixture of precursors and probably the inclusion of cadmium ions in the cationic sublattice, the result becomes drastically different. So here for the efficiency for all the doped samples after 3 hours, the efficiency of the photodegradation is of 50% or higher. And for the pure zinc oxide, it does not exceed the 23% mark after 3 hours. We also calculated the kinetic rate of the photodegradation, and it follows the pseudo first order kinetics in that meaning. And it is also seen here that the best kinetic rate of the photodegradation is for samples of 1, 2.5, and 10 weight percent of cadmium acetylcysteine. And the samples with 5 and 7.5 have not so good kinetic rate, which might be related to their bigger grain size and also higher intensity of the blue emission on the photoluminescence spectrum. There is in the conclusion, the results of the X-ray diffraction analysis confirmed the formation of the crystalline phase of zinc oxide of the Versite type. And Raman measurements showed the broadening of both the eta low and eta high modes at more than 5.8% of cadmium acetylcysteine, and indicated the increase in disorder in a crystal structure, and all the cadmium was not detected in EDX analysis. Photoluminescence and photocatalytic activity analysis of the microstructures growing with different cadmium acetylcysteine concentrations demonstrate significant differences to the samples with the pure zinc oxide. So it might be stated that zinc oxide microstructures obtained with atmospheric pressure MOCVD include ions of cadmium in the crystal lattice and have a high they are promising for the photocatalytic use, which might be maximized for practical purposes during the future researches. So thank you for your attention, and I will gladly answer your questions.
Okay, thank you very much for your very nice presentation, and I have some questions. First of them is, it is well known that titanium dioxide and zinc oxide are similar in the photocatalytical field. And what do you think about the, what do you could tell about the general differences in photocatalysis, zinc oxides and titanium dioxides? What is the main general differences? Because both oxides are characterized by low toxicity, relative weight band gap, and low cost. And what else? What do you think?
So for zinc oxide, it is like in its pure form, it is not as good of a photocatalyst, but doping it makes it makes the rate of the photodegradation of organic pollutants better. But for titanium oxide, I guess it's well, I know that it has better rates of photodegradation in the field. However,
Oh,
I
okay.
can't tell you about the drastic differences. So I concentrate on the zinc oxide in my research and not on titanium oxide, as I saw that the titanium oxide is already used in that field widely.
Different morphologies, maybe.
Yes,
Okay.
yes.
And what is the mechanism of the fixation cadmium in the zinc oxide matrix? It's in cationic form or formed in other phases?
So it's an isovalent dopant. So in the crystal lattice of the material, it replaces the zinc atoms by it, but it deteriorates the crystal lattice as it has a bigger radii of the atoms than zinc.
Okay, thank you. And the last questions about the solutions do you use for the testing of photocatalytic properties of your composite?
For the photocatalytic properties, it was the water solution of the methyl orange. So we just use the water solution of the methyl orange and irradiate it with the mercury lamp, ultraviolet mercury lamp.
And what concentration do you use for experiment? Concentration of the solution and mass of the photocatalyst.
So for the mass of the photocatalyst, it was the square of microstructures of 1.5 by 1.5 millimeters. And so I don't know about the mass, but the square of the area of the sample. And for the solution, the concentration was around 20 milligram or 200 milligrams per liter.
Usually 10 or 20 milligram
Yeah,
per
20
cubical
milligrams per
decimeter
liter.
usually
Yeah,
used
the initial
for.
concentration. Yeah.
Okay, thank you very much. Has a question? Oh, yes. Okay, we have one question from the hall. Please. Okay, do you hear me? Yes, can you hear me?
Hello? Hello?
Oh, yeah, now I hear you.
Now it's better again. So, Alexander Vassiliev here. My question is maybe a little bit more distant from what Dr. Lavernenko just asked. It's more on the cadmium. Yeah, cadmium. If I'm not mistaken, it's a critical raw material, and it's toxic. Are there any options to modify the properties of zinc oxide films instead of cadmium? Did you look into what is possible with maybe less toxic or less raw material, less critical raw material?
So yeah, the only downside of the use of the cadmium is its toxicity. But zinc oxide might also be doped with magnesium, which is also the isovalent doping of it. However, if I'm not mistaken, it widens the band gap of the material and does not sorry, I forgot the word. So it does not narrow it. So at the moment, we didn't look for the other dopants of the material, as we wanted to see if the method of the atmospheric pressure emulsivity can be used for this purpose. So it was the initial aim of the research, to see if the method can be used for to obtain the microstructures for this purpose. As the atmospheric
okay,
pressure
so
emulsivity is easier to make than the usual emulsivity with vacuum.
One more, a follow-up?
Yes,
I
yes.
will be enough for, well, because really I agree with Dr. Alexander Vasilyev, because when do you use the cadmium and included it in the zinc oxide matrix, you increase the toxicity of your composites and practical application. It's in the future.
No, it's probably okay. My follow-up question is it something very new, or is it a modification of something that exists and you just want to improve it? Because I'm not a specialist in the area, so my questions are mostly naive. Excuse me, please, but could you please satisfy my curiosity?
It's more of an improvement, as other methods are used to dope the zinc oxide with cadmium, as the magnetron resonance, electronic resonance, or the usual emulsivity. And we wanted to use the atmospheric pressure emulsivity. However, we obtained the results we did not expect, as we expected the doping to be more evident in the, for example, the EDX
I'm sorry to interrupt you.
analysis.
I'm sorry. I'm really sorry. But that's it was poor formulation
Connection.
of my question. I mean, do other people use the same composition? Zinc oxide plus cadmium. Is it an
Yeah,
industrial standard or something like that? Not standard, but how ubiquitous it?
I don't know about the industrial standard, but I saw different researches which use cadmium doping for zinc oxide to change its structure, obtain materials like the crystals with specific structures, or to make the cadmium doped zinc oxide for different purposes, like for the band gap engineering, just using other synthesis methods, so not atmospheric pressure MOCD.
So it's more or less established system where you are trying to do something unique.
Yes, yes.
Okay, thank you. Thank you.
Okay, thank you very much. Are there other questions in the hall? No online questions? No? Okay, thank you. We will thank you again. Okay, and your diploma here. If do you want to obtain it, you will come to us.
Yes.
Okay.
Thank you.
Okay, thank you. Our next speaker is Alina Litvinenko from Bogomolets Institute of Physiology, National Academy of Science of Ukraine. Alina, are you here?
Good afternoon. I am online, but I cannot.
We don't see your presentation.
Okay, please 1 second.
Okay, you're waiting. Now we will see only your name.
Excuse me, it's some problem. Please.
Yeah, small problem, but.
1 minute.
No, okay. No.
Okay.
Oh, yes. We will see your presentation. Okay, please.
Greeting to all participants and organizers of the conference. Thank you for the opportunity to speak and present our research. I also read the program and have already listened to several interesting and very informative presentation here today. Thank you. Our work were carried out in the Bogomolets Institute of Physiology, Ukraine, and there seem to be a few such works. In fact, such a work is the only one, is not it? Therefore, I want to note right away that our research is about what could happen in an animal body if nanoparticles or nanosystems are introduced in some way. I would be grateful for questions. You can write them, ask them, but not at high speed because I am still learning English. But I will try to understand and answer. Thank you for understanding. Okay, so as is well known, nanoparticles are a fast, constantly expanding drug delivery and diagnostic field, rendering infinite combination and possibilities. The slide visually presents the nanoparticles classification. And therefore, nanoparticles classification can be based on their composition, categorized into 4 groups: inorganic, organic, carbon-based, and hydrogen nanoparticles composed of a combination of organic and inorganic materials. Okay, so the figure illustrated schematic representation of the difference routes for nanoparticles drug delivery with attention to the oral administration and the interaction with the intestinal barrier. Over the past decade, new generation of nanoparticles have emerged that are capable of performing additional delivery function that can enable treatment via new therapeutic modalities. In the current clinical landscape, many of these new generation nanoparticles, in particular silver, has become extremely widespread in the medical, food, and pharmaceutical industries. A number of preparations with antibacterial, antiviral, and antifungal properties have been created based on colloidal silver. Application of nanoparticles in intestinal health actively studied now. The photo shows the schematic illustration of engineering nanosystem for regulation female reproductive system. Today, the impact of various nanosystems on reproductive function is being actively studied. This includes disorders such as endometriosis, polycystic ovarian syndrome, and premature ovarian failure. However, the effects of silver nanoparticles on the intestine and reproductive system have not been sufficiently studied. The aim of the work was to evaluate the effects of silver nanoparticles on small intestine cell and cell of the follicular environment on all sides under conditions of experiment premature ovarian failure and the use of resveratrol in female mice that has not been studied before. First of all, we would like to express our gratitude for the cooperation and provision of silver nanoparticles in a polymer matrix to research from Shevchenko University, namely Natalia Kutsevo and Yulia Kuziv. Synthesis of these silver nanoparticles has been performed using particularly hydrolyzed star-shaped graft copolymer of polyacrylamide to dextran and as auxiliary camping agent. The star-branched copolymer proved to be a very good template for nanoparticles synthesized due to high local concentration and functional groups. Detail of synthesis, identification, and analysis of silver nanoparticles are described by Kutsevol in Journal Structure Chemistry journal. Formation of silver nanoparticles was confirmed with transmission electron microscopy. Exemplary transmission electron microscopy images of silver nanoparticles synthesized in presence on the anionic copolymer pH7 are present in figure 1 and B. The image shows that the obtained colloids contain mainly a small portion nanoparticle clusters. The nanoparticles are sized from 10 to 60 nanometers. It should be noted that transmission electron microscopy images resolution was not sufficient to register very small nanoparticles, less than 4 nanometers in size. You can search for all questions, comments, and suggestions regarding the use of these nanoparticles in the publication listed and ask other colleagues in writing. Experiments were carried out using white laboratory female mice of the albino line, 10 weeks, 22 grams. According to the Geneva Convention, International Guiding Principle of Biomedical Research Involving Animals, and have been approved by the Biomedical Ethnic Committee of Bogomolets Institute. Research growth. First, control. Second, experimental premature ovarian failure, EPOF, in mice. It was groups of animals number 2, 3, and 4. This model was created by immunization with kidney antigen suspension obtained from the mother. Immunization was carried out 4 times, intraperitoneally once a day at the rate of 2 microliters of suspension per 2 gram of mouse weight according to the following scheme. On the 1st, 3rd, 5th, and 26th day, 4 weeks after from the beginning of the experiment. Searchers group, it was animals with EPOF and treatment with silver nanoparticles. Silver nanoparticles were treated intravenously at a dose of 2 micrograms per kilograms once a day, 3 times, starting the day after the last immunization with kidney homogenate suspensions. Fourth group with experimental premature ovarian failure and treatment with silver and resveratrol. Resveratrol at a dose of 50 milligrams per kilogram was administered intraperitoneally once a day, 3 times, starting the day after the last immunization, 1 hour after intravenously administration of silver nanoparticles. Isolation of enterocytes was carried out according to the Kimura, by which a suspension of epithelial cells was obtained from upper part in the ileum villus. To determine the parameter was viability and Dell's pathway of enterocytes and cells of the follicular environment of oocytes. Sampling of experimental material from female mice, intestine, and ovaries was carried out under anesthesia the day after the last administration of silver nanoparticles. The methods of color fluorescent dyes, the apoptotic and necrotic cells of enterocytes and follicular environment of oocytes cells was estimated by morphological characteristics using the vivo methods of two-color fluorescent nucleic acid dye, HOXT and rubidium iodide. The condensation and fragmentation of nuclei was occurred during apoptosis can easily be detected with fluorescent DNA binding cues such as HOXT and rubidium iodide. Cells stained in this way can then be counted with apoptotic nuclei displaying characteristic hypercondensation and fragmentation into distinct globules. Contrast, necrotic cells display a slow, swollen, decondensant morphology that is very distinct from the features exhibited by apoptotic nuclei. For the statistical analysis of the results, the software package GraphPath Prism version 10 for Windows were used. So, as a result of our research, we obtain the following results. This slide shows change of DELS enterocytes. Under experimental premature ovarian failure, it is second column, we saw that decrease the number of live cells of the ileum on small intestine and increase the number such cells with apoptotic and necrotic. The introduction of silver nanoparticles, it is three column, under experimental premature ovarian failure and silver nanoparticles condition had no effect toxic. Certain change in the viability of enterocytes were observed. However, no statistically significant change in the number of necrotic cells. Under the YPOF and use resveratrol, antioxidant, and silver nanoparticles, we saw increase the size of lymph cells, enterocytes, and increase the number of cells with apoptotic and necrotic sinks. New data of effects of silver nanoparticles on small intestine cells have been obtained, encourage further research, possible therapeutic treatment of such nanoparticles. In cells of follicular environment, we can see some same changes. There was a decrease in number of living cells and increase the number with apoptotic and necrotic sinks in the model of experimental premature ovarian failure. We have shown for the first time that the introduction of silver nanoparticles under this condition leads to a suppression of the viability of follicular environment oocyte cells. Specifically, the proportion of live cells decrease, and while the proportion of cells with morphological sinks, apoptosis and necrosis increases compared to the same values in animal with YPOF group. It was established for the first time that under experiment premature ovarian failure condition and use silver nanoparticles and resveratrol causes a growth number of lymph cells and reduce the proportion with apoptotic and necrotic. Our data indicate that resveratrol has a positive effects on folliculogenesis in the setting of experimental premature ovarian failure and the initial stage of chronic kidney disease when there is already kidney damage, accompanied by impairing filtration and manifestation by proteinuria. Further studies are needed to clarify the mechanism of action of silver nanoparticles and resveratrol as a therapeutic agent for influencing ovarian cells and oocytes in the setting of experimental premature ovarian failure. In general, for better understanding, let us to illustrate these results of our work as follows figure that illustrates nanotoxicity results from expression of free radicals production, which introduce oxidative stress. Oxidative stress causes lipid peroxidation, protein oxidation, and DNA damage, which together enhance the inflammatory response, causing various inflammatory pathways. On the other hand, activation of antioxidant defense, such as through and administration of antioxidant, reduce reproductive nanotoxicity. So we have some conclusion. Under the EPOF condition and the introduction of silver nanoparticles, an additional decrease the number of leaf cells of the follicular environment of oocytes and increases the proportion with such cells with morphological synthesis of apoptosis were found, and under experimental premature ovarian failure conditions, the use of resveratrol after silver nanoparticles leads to an increase the proportion of leaf cells, enterocytes of the ileum on the small intestine cell and the cell of follicular environment oocytes, as well as decrease in apoptotic such cells. New data on the effects of silver nanoparticles on small intestine cell and cell of the follicular environment of oocytes have been obtained, encourage further research possible therapeutic treatment of such nanoparticles. So we would like to thank Natalia Kutsevova and Yulia Kuziev for give this as nanoparticles, and thank you for your attention. Thank you.
Of nanoparticles in biology and medicine. My question is about the, do you study the toxicological activity and toxicological impact of the nanoparticles on body tissues? Toxicology.
Okay. This is nanoparticles was characterization by Skutevol, and they was carry out investigation into nanotoxicity, and this is nanoparticles don't have nanotoxicity, but we in our research in reproductive female system in mice, we can see that they have increase number cells with apoptotic and necrotic. So it's is a result from some DNA damage, oxidative stress. So these nanoparticles must be investigation in further research.
Okay. And how do you prevent the agglomeration of the particles in the body tissues? Agglomeration, yes.
In our research, we this is nanoparticles was not agglomeration. They was only clusters, some clusters, but we introduction to them with protocol of other colleagues.
Okay, understand. Yes, maybe around the particles core are formed the shells from organic species. Okay, and what do you think about removing mechanism of the nanoparticles from body of the animals? What mechanism removing such composites?
I think no, we think that now research into nanoparticles in all areas of physiology is a country very active, and there are many mechanisms of their action. And in our hands, we saw that they can change regular cell deaths. It's very important because it is maybe a new marker from the homeostasis in organism. For example, intestine and reproductive system and quality of oocytes. So in our research, we can say that these nanoparticles cause increase cells with apoptotic and necrotic sinks.
Okay, thank you very much. Dear colleagues, do you have the questions? Yes, okay, we have the question in the hall.
What methods did you use to synthesize silver nanoparticles? And the second question is, are they stable in air?
Please, the second question, can you repeat?
Are they stable in air?
They're stable in the air.
All question about nanoparticles, about the synthesis, administration, and identification, you can write for us and our colleagues, because we carry out only experiment on animals, and our research is unique because it is the effects of the body in animals, not only synthesize administration, but we focus on effects of the effects on the animals.
Okay, I understand. Thank you.
But you can write to us, and we, with our colleagues, can send you this answer.
Yes,
more
yes,
detailed.
My colleague will ask about the formation of oxidative film on the
yes.
surface of the particles, because argentum on contacting with air may easily
Yes.
oxidation. And yes, okay. Thank you. We have the questions and other questions. No questions in our hall. Okay, in the online questions. No questions. Okay, we thank you again for your very nice speech. Okay, thank you. Your
Thank you.
diploma here. Your diploma here. Certificate.
Thank you.
Okay, thank you. And now our last speaker, Rostislav Terehov from Usikov Institute of Radiophysics and Electronics, National Academy of Science. Rostislav, are you here?
Yes, I'm here. Can you hear me?
Okay, okay, okay. Please
Yes.
share your screen, your presentation.
Yep. Can you hear it?
No.
Can you see
yes,
it?
okay, we see it. Okay, thank you, please.
Okay. Dear colleagues, thank you for the opportunity to send you this message. For your attention, a report of the topic increasing the sensitivity of the surface plasmon resonance sensor based on the Gresham configuration using Maxen nanomaterial. Modern sensors based on the phenomenon of surface plasmon resonance shows low sensitivity, which is insufficient for determining small concentrations of active substances in the solution. resulting in low measurement accuracy. Recent studies on this topic show sensitivity in range from 80 to 123 degrees per refractive index unit. So the objective of the study is to enhance the sensitivity of surface plasmon resonance sensor through the modification. I aim at studying a low concentration of biomolecular solution. To achieve that goal, it was decided to use MAXEN material to modify the sensor surface. Main properties of the material, thanks to which it was possible to achieve increased sensitivity, is high electrical conductivity, which does not interfere with the extinction of the surface plasmons, and that helps to localize electromagnetic distribution at the metal dielectric interface. And also functionalization of the T surface increase the local refractive index and or promote stronger field localization. Surface plasmons are coherent oscillation of the electron density and electromagnetic fields that propagate along the surface of a metal, particularly in the thin films. They arise under the influence of the light, which causes oscillation of the electrons, creating waves that attuned in a solution from the surface. Interaction between molecular on the surface change the characteristic of the plasmons, making them basis on the surface plasmon resonance method. When light interact with the surface on the metal scene, it extends the surface plasmons. This oscillation are sensitivity to change in the refractive index in the immediate vicinity of the surface. MAXEN is a class of two-dimensional inorganic materials formed from MAX phases by selectively each and one of the components. MAXENs combined from the carbides, nitrates, or carbonitrates of transition metal and have chemical groups on their surface. They are known for the combination of the high electrical conductivity, hydrophilicity, large surface or specific area, making them promising from many applications such as batteries, supercapacitors, catalysts, and sensors. MAXEN is obtained by leaching the A component from MAX phases, as I already said, where A is, for example, it's aluminum or silicon, and M it's a transition metal, for example, titanium, molybdenum, etc. This procedure removes the A element, leaving a two-dimensional material. Key characteristic of the MAXEN, it's a two-dimensional structure. This consists of atoms in layer providing a large surface area and high accessibility for the ions and other molecules. High electrical conductivity, they combine the properties of the transition metal and hydrophilic groups, making them effective for energy storage and in electrical devices. And hydrophilicity, the precursors of the hydroxyl or oxygen groups on the surface allows to disperse stability in the water and interact with other materials. The sensitivity of SPR sensors is determined by the ratio of the resonant angle shift to the change in the refractive index of the medium band studied. In Kretschmann geometry, resonance occurs when the projection of the wave vector of the incident wave onto the boundary coincidence with the wave vector of the surface plasmon wave. If refractive index of the medium increases, the electrical constant of the also increased. This leads to increase the wave vector of the surface plasmons because the plasmons wave becomes slower in the it has a large wave vector along the surface. So increases in the refractive index of the medium shifts the resonance angle towards higher values. Determining the thickness of the silver film is necessary to establish the minimum wave reflection value at the resonance points. This increases the maximum amount of energy transferred to the surface plasmon. Also, taking into account future losses from modifying the metal dielectric boundary, it is necessary to prepare the most favorable conditions. To do this, we simulate a sensor with different silver thickness to determine the optimal thickness. The results you can see on the figure 2. Based on this result, we choose a thickness of 55 nanometer for silver. The addition of the MAXEN layer invariably leads to losses in the energy transferred to surface plasmons due to the modification of the boundary. We simulate sensor with a different MAXEN thickness to determine the optimal. The results you can show on the figure 2 and 3. It will say that we achieved the high sensitivity. To get ahead of myself, I will say that we achieve the maximum sensitivity at 6.95 nanometers of MAXEN, but the quality factor of the resonance structure was too low. So we choose thickness of 3.98 nanometers. So as you can see on the figure 1, with the increase of thickness of MAXEN, clearly increase the sensitivity of sensor up to 150 degree per refractive index unit. Figure 3 shows the resonance of the structure with the maximum sensitivity, which we achieved, but the quality factor of the structure is too unsatisfactory, and the minimum reflection at the resonant point it 0.7, which may complicate to its visibility on the instrument when conducting the experiment. So we set it on the result shows on figure 2. We have the sensitivity which 139 degrees per refractive index unit. The quality factor remains satisfactory, and the minimum at the resonant point of reflection in the resonant point was lower. Also, you can see distribution of the electric field at the resonant angle. As you can see from the figure, from the slide, surface plasmons are extinct. Energy is transferred to the surface plasmons, but part of the energy is reflected, as evidenced by the previous graphs. Also, you can see the main results of the study with the slide of conclusion. Our goal was achieved, which sensitivity increased by 52%. If we take the maximum value of sensitivity we achieved, to increase the increase of the increase in sensitivity range from 65 to 88% compared to the works of our colleagues. So that's all. Thank you for your attention, and please ask questions.
Thank you very much for your presentation. It was very interesting for us. And the only one small question about the plasmonic properties of your MXene composites. What elements do you use to supply the plasmonic properties on your composites? Thank you.
We use MXene, which is titanium-free carbon-2 TX MXene. This MXene shows us pretty good electrical conductivity compared to the other MXene, so we choose this one.
Okay, thank you. Other questions in the hall? No questions? Okay, and the questions online? Our colleagues online, no questions? Okay, maybe. Thank you very much. We thank you again for your very interesting speech. Okay, thank you. Okay.
Also, thank you for opportunity.
Yes, thank you. Also, our symposium for low dimension and nanomaterials not finished because after coffee break we will listen the presentation, 8 presentation in our session. Will be okay, and I will thank my colleagues for very hot, interesting discussion, because this symposium was very hot. Okay, thank you very much, and I invite you to go to the coffee break. Thank you. Начинаем. Okay, dear colleagues, we will continue our symposium on low material and nanomaterial. And now we will start the maybe most interesting part of our symposium. It will be the presentation, poster presentation. And our first presenter is Viktor Zaryansky from Working Institute of Low Temperature Physics and Engineering, National Academy of Science of Ukraine. Oh, okay, Viktor, are you here? Okay, please, 5 minutes, please.
Good evening, good afternoon, dear colleagues. My report title, Photoluminescent registration of new substances based on fullerite C60 obtained by chemical interaction with hydrogen and nitrogen molecules. Single crystals of C60 saturated with molecular hydrogen and nitrogen were studied using the spectral luminescent method of registration in the quantum Compton mode at low temperature of 20 Kelvin. Previously, it was found the temperature limit of the adsorption crossover for fullerite C60 in the hydrogen and nitrogen atmosphere. Adsorption crossover is transition from the diffusion mechanism of intercalation to chemical interaction. For hydrogen atmosphere is about 250 degrees Celsius, and for nitrogen atmosphere is about 420 degrees Celsius. At saturation temperatures above this indicated, the process of chemical interaction of impurity molecules and the fullerite matrix occurs with formation of new compounds. Therefore, saturation was carried out at a temperature of 300 degrees Celsius for hydrogen and 450 degrees Celsius for nitrogen and the pressure of 30 atmosphere. The formation of new chemical substances with their own radiative properties different from the luminescent properties of the initial materials is recorded. In particular, opposite transformation of electron energy spectra and the changes in quantum yield are established for cases of hydrogenation and nitridation of fullerite C60. It is shown what in the first case a mixture of fullerants with the close hydrogenation index is synthesized. With the spectrum shift to the high energy region and simultaneous increase in luminescence intensity. In the case of reaction of C60 with nitrogen, a multi-component complex of nitrided fullerenes is formed. The overall spectrum of these is shifted to the long wave region with pronounced low temperature quenching of emission. Analysis of the blue shift of the hydrogenation fullerite spectrum showed that hydrogen chemisorption at temperatures close to the adsorption crossover temperature leads to the synthesis of weakly saturated fullerants with a degree of hydrogenation from 8 to 14. It was also found that the characteristic structureless luminescence of other fullerene dimer or biazofuran is present in spectra of the reaction product of C60, this nitrogen. Its maximum almost exactly coincides with the position of the first band in the spectrum of the new shape of the shortwave shoulder apparently makes the main contribution to the intensity of beginning of the spectrum. Thank you for attention.
Thank you very much. Dear colleagues, the questions, please. There are no questions. Okay. Thank you very much for your speech. Okay, thank you. Our next presenter is Lina Sartinska, Francevich Institute for Problems of Material Science. Please, Lina. Okay. Oh. No. Oh, okay. Next. Our. Okay. Come, Vitaly Karpina is our next presenter, please.
For everybody, I will present our.
Please, Michael. Yes. Okay.
Having a wide direct band gap and the unity combination of electrical and optical properties, silicon oxide is considered as a prospective material for many applications, including photocatalysis. In order to improve photocatalytic activity of silicon oxide films and nanostructure, one can apply the doping by various impurities. And magnesium is the best choice for this purpose. In this work, we compare the properties, structure properties by Raman measurements and photoluminescence property of outgrown silicon nanostructure and annealed. The silicon nanostructure were grown by atmospheric pressure, metallurgical chemical vapor deposition from acetyl acetonase of magnesium and zinc in appropriate concentrations. The morphology of obtained silicon nanostructure you can see on the screen. In the Raman spectra, there is intense line related to crystal lattice of silicon oxide, such as E2 low, E2 high, and the E2 low minus E2 high, as well as with minimal concentration of magnesium. You can see also longitude optical and transverse optical oscillation, A1LO and A1TO. With increasing magnesium doping, this line is diminishing and some disappear. But annealed samples demonstrate increased crystal lattice, but without A1LO oscillations. In photoluminescence spectra, you can see the near band edge emission, very intensive, which is also diminishing with magnesium doping, but without great emission in visible range of spectrum. But annealed samples demonstrate intensive deep level emissions related to oxygen vacancies in silicon lattice. The intensity of it is comparable to intensity of near band edge emission. And this indicates on good properties for photocatalytic applications. Thank you very much.
Please, thank you very much. And please, your certificate of the participant. Okay. Yes, okay. The first presenter who the certificate. Thank you. Thank you. Our next, maybe may you switch off because okay. Yes, because we listen. Okay. Our next presenter, Sergey Lisavenko. Are you here, Sergey?
Yes, I'm here.
Okay, please.
Good afternoon, everyone. My name is Sergey Lisavenko, and I am presenting the result of our work simulation of the structure of liquid alloys with quasi-force algorithm using the experimental X-ray intensity curve. Information about the local atomic structure formation in liquid alloys is essential for understanding the impact of the temperature component content, nature of the nucleation, crystal growth, and formation of stable and metastable solid phases. The aim of this work was to update the quasi-force method for simulation of liquid alloys using an experimental X-ray intensity curve. The principle of operation of quasi-force algorithm is movement of atoms in the direction of the fastest decrease in the mean square deviation of the model structure factor or intensity curve from the experimental data. The quasi-force in our case is a negative gradient of the mean square deviation in the experimental intensity curve from the model 1 as applied to a given atom. To find this gradient, the X-ray intensity curve of scattered radiation for the model are calculated at small displacement of the given atom in the three mutually perpendicular direction, which consists with directions of the coordinate axis. The X-ray intensity curve of the simulated macrocell is calculated by using the kinematic diffraction theory. The scheme of the quasi-force algorithm is shown on this slide. For the initial model, an intensity curve is calculated and its discrepancy with the experimental one is found. A quasi-force is calculated for each atom. The model must have central spatial constraint, must have certain spatial constraints. Compliance with them is achieved by introducing additional forces. This can be obtained either from a hard sphere potential or from Lennard-Jones potential. They are selected according to atomic radii of the components of the fluid under study. Next, the quasi-force are combined with the force responsible for the spatial constraints. Then the forces are scaled to achieve a given pressure in the modeled system. From the obtained forces, the acceleration of the atoms are calculated. The velocities of the atoms are calculated and scaled to achieve a given temperature for the model. The new positions of the atoms are calculated, and finally pair correlation function are calculated. They are needed both for analyzing the obtained model and for calculating the X-ray scattering intensity curve in the next iteration. The algorithm was tested on the X-ray scattering intensity curves in the nickel-mangan system. The graph of the second column, the graph in the second column shows a comparison of experimental and model intensity curves for models with different numbers of atoms. For the graphs, we see that the model with 500 atoms is already able to reproduce an intensity curve that describes the experimental one quite well. The model with 5,000 atoms is able to reproduce an intensity curve with fewer oscillation before the first peak, which is associated with so-called truncation artifact. The graph on the top, the third column, tracks the evolution of the discrepancy, chi square, between the experimental and model intensity curves. Demonstration rapid and successful convergence of the model to the experimental data and oscillates around its minimum value as the structure refines. Below it, the self-diffusion plot confirms that the atoms in the simulated nickel-mangan liquid model maintain realistic mobility, which is crucial for achieving an accurate, relaxed, and physically sound final structure. Thanks for your attention.
For next speaking, we ask Lina Sartinsky again. Lina, are you here or not? Your second presentation. No? Okay. The next speaker, the next presenter is Dmitro Melnikov. Dmitro? Okay. Okay, please.
Sorry, I am here, and I suppose that my report will be
Lina.
on the
Okay.
strategy of
Okay. Do you have two presentation? Okay.
and I am waiting for presentation. No, I'm not ready to today. I suppose that I have presentation next day on Friday.
No, according to the program, you have presentation today.
Oh, it's very. I will
Tuesday.
try. Okay, I will try to tell this presentation now. Hello everybody. My topic of my presentation: effect of surface on tuning the properties of platelet-like hexagonal boron nanopowders via oxidation. One moment. Do you listen me?
Yes.
Okay.
Yes, we are listening you. Yes, everything is okay. We listen and see your presentation. Okay.
So as initial particles, I took hexagonal boron nitride, commercial boron nitride. It is a Champer company. We investigated properties of this boron nitride before oxidation and during oxidation. We make oxidation in fantasy from 50 to 8 degrees C, 800 degrees C. And after heating, we discovered that in the X-ray diffraction study demonstrates that there are monoclinic boron oxide. Here you can see. X-ray diffraction study also demonstrated that we have very strong increasing reflection in C-axis, but for its O2 axis, but along 100 axis we have practically no any changes. And next picture, we can after this X-ray diffraction study we made in infrared spectroscopy investigation. And this infrared spectroscopy investigation demonstrated that this hydrogen impurity decrease, as you can see, and we have increased this line and ridge sheet. So boron nitrogen peak changed at the temperature 800 degrees C. And last investigation, it was investigation of band gap. Band gap, you have this to band gap at 50 temperature and 800 degrees C. When we measure, when we calculate a band gap from absorption edge minima, we get that band gap at 50 degrees C, 509, and at 800 degrees C, it's 504. Transmitted maximum is the same, demonstrated decreasing in band gap. Based on this investigation, we proposed next model of transformation during the heating from 50 to 800 degrees C. Due to heating, at the beginning we have deleting hydrogen groups, reordering because there are some changes until 500 degrees C, and after 600 degrees C we have transformation of structure. Melting boron oxide work like flux and promote formation of ordering structure along C axis. Based on this investigation, we demonstrated connection between properties and the structure.
Lena, please, 5 minutes. Your time is over.
It's finished. Due to heat treatment, we can manage band gap and structure of our initial particles, boron nitride particles. That's all that I want to say.
Okay, thank you. And would you like to present your work or not?
Yes, I can present.
Okay, please, 5 minutes to.
Okay.
Okay, but we don't see the second present. Okay, please.
It's not my presentation.
У нього дві презентації. Тобто перша, це була друга, це?
Because I suppose that I should make presentation on Friday.
Вона була третя чи друга вона була. Ось вона.
No, it's
А це те саме, це було як, а в неї ще друга, ще вниз тоді йдемо.
Ага.
Зараз ми шукаємо. Вона була перед витром.
This, yes, okay. So next presentation.
Okay.
I want to say next presentation topic is properties of boron nitride resulting from incomplete synthesis. We took two particles, initial particles, boron particles. It's pure particles with size 550 nanometers and more coarse particles 200 nanometers. But this coarse particles has additive of carbon and boron oxide. We carry out heating in optical furnace, high power optical furnace in current in flow of nitrogen. After heating, temperature is very high temperature gradients, and we got platelet structure and equiacid structure. And analysis, X-ray diffraction analysis demonstrate, and it will the calculation demonstrate that first particles, nitride particles, and second nitride particles has approximately the same composition, boron nitride or boron oxide, boron with increased boron content, boron nitride with increased boron content, and the second particles, coarse particles, has also additive phase, boron nitride with increased boron content and has some amorphous phase. Infrared diffraction study demonstrated that these particles has hydrogen component and has oxygen component beside boron and nitrogen. So based on this investigation, we propose next model of our particles. It is on the surface sessolide, because we have hydrogen on the surface, then boron oxide, then boron nitride beneath boron oxide, then boron nitride with increased boron content, and inside we have boron. So look like coral shell structure, but it's layered structure, or maybe not layered, because these layers may be not so nice like at this picture. Then after that we investigated properties of this particles, and it was demonstrated that coarse particles demonstrate equiaxic particles demonstrate higher luminescent properties, and platelet particles has lower luminescent properties because of structure. And next investigation, our paramagnetic properties. Paramagnetic properties are different from these particles. Particles, equiaxic particles, has lower intensity of paramagnetic signal. Compare with, if you can see this difference. And moreover, G factor of this equiaxic particles closer to G factor of free electron. So based off this investigation, we can say that particles produced at high temperature, and a high temperature gradient has complicated coral shell structure, and their properties depend on the structure, or this equiaxic structure, or this structure is the platelet structure. Band gap investigation also demonstrated that platelet structure has the same band gap 5.9, and this band gap was approximately 504, a little bit lower than another structure, than platelet structure. So you can see effect structure on the properties of material, of powders. That's all.
Okay, thank you very much. And now I will invite Dmytro Melnikov from National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnical University. Please. Microphone. Okay. Okay, microphone.
So today I will introduce influence of hydrogen annealing on the order L10 phases formation in nanoscale ferrum, platinum, palladium with layer of silver field. So motivation is nanoscale fields can I 1 second take, because you can even see what happened there. Yeah, thanks. Please. So nanoscale films based on ferrum platina and ferrum palladi. Alloys with an order L10 have a promising material for ultra high density magnetic information cameras, carriers, sensors, and spintronic applications. A key difference between palladium and platinum is ability of absorbing hydrogen, like the solubility of hydrogen in palladium is around 0.7 H per palladium at H2 pressure of 1 atmosphere and room temperature, while for platinum is negligible around 10 power minus 11 under the same condition. The purpose was to determine the effect of the heat treatment in the hydrogen environment and the silver addition on the phase composition and structure of the films. Nanoscale films with 50% of ferrum and 50% split between platina and palladium, 75% of platina and 25% of palladium. You can see, can I show like this, how it will work today? Mm-hmm. Yeah. Okay. Ничего я не выпускал. О, сделалось. So you can see the how composite looks like. We have a film with total thickness of 15.9 nanometers, obtained by magnetic sputtering on a silicon oxide tool, this layer, and with just silicon substrate at room temperature. After depositing the film were annihilated in the hydrogen environment at the temperature 300 to 900 Celsius degrees for 1 hour. The process of the A1 into L10 phase transformation were investigated by X-ray diffraction and RHE method. Here's showed the changes of the film by heat and treatment. And there's as a result of X-ray diffraction and RHED. So, as conclusions, in acid deposit films, disordered A1 phases with FCC structure was observed. The order L10 phase in the film begins to form at 400 degrees. You can see here we have a superstructure beginning create 400 degrees Celsius. As the temperature rise up to 500 degrees, it's almost its amount increases, and RHED method confirms the X-ray data. The silver editing activates the ordering process and contributes to increase the order degree. The degree of ordering of the L10 phase almost don't change in annealing temperature range between 500 degrees and 900 degrees. The C parameter sign increased with increasing annealing temperature due to hydrogen diffuse. So yeah, and decreases in CA ratio indicate and increases of the degree of tetragonality. So that's it. Thank you for.
Okay, thank you very much for your very interesting presentation, and let me take your certificate of the participant. Okay, thank you. Yeah. Our next speaker is Yuri Yevorsky, the Technical University of the Ukraine, Igor Sikorsky Polytechnical Institute. Please.
Thank you. Good afternoon, dear colleagues. First of all, I would like to thank the organization committee of the conference for the excellent organization of the conference and for giving me opportunity to speak today. I will try to brief present the result of my studies. So on this slide, you can see the main findings of the research titled such like impact of mechanical treatment duration on the nanopowder composite based on the transition and semi-metal oxides, illustrated on the example of the nanoscaled mixture of titanium and silicon oxide. The relationship between the electronic structure, crystalline parameters, morphological features of the nanopowder mixtures and electrochemical characteristics of the prototype battery of cathode based on these two oxides was established. Moreover, I have to say that in this slide you can see only the result of one group of the investigations, but we have another ones which show the result of this experimental investigation of mixtures based on oxide of silicon and aluminum and ferrum oxide and so on. To determine the structure features, we use scanning electron microscopy, X-ray diffraction, ultrasoft X-ray emission spectroscopy, and for determining the electrochemical characteristic, we use galvanostatic and potentiodynamic analysis. It was found or concluded that this mixture, CO2, TO2 nanopowder, after mechanical synthesis treatment during the 5 minutes, reveal most promising electrochemical characteristic in terms of possible application in primary and secondary power sources. This result is caused by the desorption of adsorption moisture, the grinding of the initial agglomerates, and formation of high charge state of oxygen due to the creation of weak p-bonds between the nanoparticle surface of both oxides during such brief treatment. But further increasing of processing duration promote the agglomeration of the nanocomposite and significant reduction of electrochemical characteristic of lithium power sources. Moreover, I want to say that we have some dependence between the electronic structure of the material or p states of created composite and electrochemical characteristic of the composite. Mostly that is the capacity and power in galvanostatic mode of such composite. In general, that's all. Thank you for your attention. if you have any question, I would like to answer
Okay,
them.
thank you very much, but we have not possibility to ask you questions. Okay, thank
Okay,
you,
thank you.
and thank you. And our last presenter is Vitaly Lubachka from the Institute of Solid State Physics and Chemistry, Uzhgorod National University of the Ukraine. Please, Vitaly, are you here?
Yes, I'm here.
Okay, please, 5 minutes. Okay, we are listening here.
Okay, good afternoon once again. The topic of this presentation you can see on your screens. So, research into two-dimensional van der Waals materials has seen significant growth in recent years, with interest focusing on various types, including insulators, semiconductors, and materials with correlated electron properties. A novel family of layered ferroelectric compounds, namely copper indium P2 S6 crystals or copper indium P2 selenium 6 crystals, has emerged as a promising candidate for two-dimensional materials exhibiting ferroelectric properties. A methodology employed for the study of ferroelectric properties is a quantum anharmonic oscillator model, which has been instrumental in analyzing the ferroelectric properties of materials on an atomistic level. The quantum anharmonic oscillator model is predicated upon phonon-like bosonic excitation, thereby facilitating a more profound comprehension of the manner in which quantum and thermal fluctuations impact the nonlinear dynamics of copper and indium through the lattice, as in our systems, the cation is mainly responsible for the ferroid properties. The present study analyzes the temperature evolution of the pseudospin fluctuation spectra of copper indium P2 selenium 6 compound and compares them with already analyzed copper indium P2 S6 crystal. These comparisons facilitate a more profound comprehension of the cation's role in the ferroelectric properties when substituting from sulfur to selenium in the anionic sublattice. In order to facilitate the analysis within the quantum anharmonic oscillator model, it is necessary to solve the Hamiltonians of such systems. This analysis suggests three possible solutions, one stable and two metastable. Here we present the calculated temperature evolution of the spatial distribution for copper and indium cations, and hence their displacements. In the present system, the concept of pseudospin is employed in the context of the ordering of copper cations and the displacive dynamics of indium cations. The temperature-dependent spectral transformations observed in the ferroelectric phase transitions of both compounds are attributed to the second-order Jahn-Teller effect, which results in the displacements of copper from the center of the sulfur or selenium octahedron. This displacement is caused by the hybridization of electron orbitals. In the monoclinic phase of copper indium P2 S6 crystal, a part of the copper cations can be thrown out into the van der Waals band gap. However, this phenomenon does not occur in trigonal copper indium P2 selenium 6 due to the short-range repulsion, which limits the magnitude of the displacement. Consequently, the local potential wells of copper cations in the selenide compound become shallower than in the sulfide, reducing the transition temperature from 315 K to 235 K. The obtained results evidently reflect the thermal properties of layered copper indium P2 6 or copper indium P2 selenium 6 crystals. Also, the calculated pseudospin spectra are in a good agreement with the Raman studies performed by my colleagues from my department. So that's all. Thank you for your attention.
Thank you very much. Dear colleagues, we finished our symposium on low dimension materials and nanomaterials, and I take the microphone to our colleagues, Dr. Marina Staroshenko, to continue our meeting.
No. Currently, the chair of the Symposium of Advanced Ceramic and Glasses, Professor Yuri Bohomol, will chair this flash poster session.
Thank you. Here. Dear colleagues, good afternoon. We can start our evening symposium named Advanced Ceramics and Glasses. And our first presenter is Viktor Goncharuk from Fransevich Institute for Problem of Material Science. Viktor, are you here?
Dear colleagues, my name is Mykola Yefimov. I make this presentation instead Viktor Goncharuk.
Okay, no problem. Please, you can start. 5 minutes, please.
Thank you. Dear colleagues, let me to present you the report using thermomechanical treatment to improve the mechanical properties of silicon and silicon-based ceramics. This study investigates the possibility for stress relaxation near cracks in silicon and silicon-based ceramic and applied internal load and temperatures close to ductile to brittle transition temperature. It was assumed that a result of thermomechanical treatment, preliminary stress relaxation around defects in ceramic occurs, resulting in increased strength and fracture toughness of the material. Based on the concept of the characteristic deformation temperature and an analysis of experimental data on the temperature dependence of the mechanical properties of covalent crystal and refractory compound, and the general scheme for the temperature dependence of mechanical properties was proposed. In ceramic materials, a maximum fracture stress is observed near the ductile brittle transition temperature. Consequently, preliminary loading of the materials, silicon and silicon-based ceramic, and a temperature close to the ductile to brittle transition temperature should preliminary cause stress relaxation at the crack tips, terribly enhanced the fracture resistance. As a result, the mechanical properties of ceramic after thermal mechanical treatment determined at room temperature significantly increase compared to the initial state of materials. For silicon and ceramic based on it, the authors proposed to perform thermomechanical treatment and temperature near to ductile to brittle transition temperature by loading the sample to a stress equal to 0.9 of fracture stress. As a result of the treatment, the fracture toughness of single crystal silicon, depending on crystallography orientation, increased approximately in 2 times, and the stress of polycrystalline silicon increased by about 1.5 times. Thermomechanical treatment applied to silicon nitride and silicon carbide resulted in increased in fracture toughness and strength by approximately 1.5 and 1.25 times, respectively. Thus, using silicon and ceramic base on it as examples, the feasibility of increasing of strength of ceramic by preliminary mechanical loading at a temperature near the ductile to brittle transition temperature has been demonstrated. Thank you for attention.
Okay, good.
Okay, thank you very much for your presentation. Our next presenter is Valery Borovik. Valery, are you here? Not here, maybe later. And our next presenter is Olena Dudnik from Francevich Institute for Problem of Material Science. Olena, are you here? Olena? No, not now. Maybe later. Okay.
From
Next
Francevich Institute.
From Francevich Institute for Problems of Material Science. Okay, no. Okay, next presenter, Alexander Vdovichenko, also from Francevich Institute for Problems of Material Science. Alexander, are you here? Also not here, maybe later. Okay. Next, our next presentation, Irina Diduk, the same from Francevich Institute for Problems of Material Science. Please.
Один.
Good day, everyone. My first presentation. Continuous basalt fibers are widely used in various composite materials. Basalt fibers has high strength, chemical resistance, non-flammability, and eco-friendliness. Modified fibers for the production of fiber composition for special application are of particular interest. The paper studies glass formation and fiber formation in silicate boron yttrium systems from andesite basalts modified with yttrium and boron oxides. The influence of yttrium oxides of the properties of multi-component aluminosilicate melts, glasses, and fibers was revealed through in-depth study of composition, structure, and properties of these systems. The introduction of yttrium oxides into rock melts without adding boron compounds is impossible. Yttrium remains in the form of non-melted agglomerates. The additional introduction in boron compounds into the melt has a positive effect on the glass formation and makes it possible to obtain homogeneous melts and glasses. The modified melts and basalt boron yttrium fibers contain 1 and 2% of weight of yttrium oxides were investigated. The viscosity, weighting, and crystallization behavior of the melts were measured. The presence of yttrium oxide significantly affects the viscosity of the melts. An increase in yttrium oxide concentration by just 1% results in nearly a twice increase in absolute viscosity values. Additionally, these modified melts provide a surface temperature range 70 degrees for fiber formation, making this suitable for industrial production. Laboratory samples of basalt boron yttrium fiber were successfully created. The modification of andesite basalt melts with yttrium oxide in conjunction with boron compounds enhances the tensile strength of fiber by 10% and increased their chemical resistance in alkaline environments by 15%. Thank you very much for your attention.
Thank you for your report. let me present you the certificate of participation.
Thank you.
Our next presenter is Alexey Lyudvichenko from Bakel Institute for Superhard Materials.
Есть комментарий. Good day. Do you hear me? No? Good day. The topic, my name is Alexey Lyudvichenko from Bakel Institute for Superhard Material. The topic of my report is optimization of the high-pressure apparatus cell thermal state for crystallization of gallium nitride from the ferrum gallium nitrogen solution melt. In recent decades, wide bandgap semiconductors have garnered increasing scientific interest due to their ability to function under extreme conditions. Gallium nitride with a wide bandgap of 3.4 electron volt is a particularly promising material owing to its resistance to high temperature and radiation, enabling electronic devices to operate at temperature up to 300 degrees Celsius. Currently, there is no viable technology for producing perfect GaN single crystals of satisfactory quality and size. Therefore, the search for an economically competitive technology for creating GaN single crystals is a pressing issue. The promising technology for obtaining GaN single crystals proposed at the Bakel Institute for Superhard Material of the National Academy of Science of Ukraine is based on its recrystallization from the ferrum gallium nitride solution melt under high pressure and high temperature condition. The first part of the work is the study of the solubility of GaN in iron and pressure up to 8 gigapascals and temperature up to 1000 degrees Celsius in the toroid 30 high pressure apparatus. The second part is to carry out GaN crystals growth experiments by the temperature gradient method at pressure up to 5 gigapascals and temperature up to 1600 degrees Celsius in the toroid 40 high pressure apparatus. The aim of this work is to optimize the process of high pressure apparatus cell resistive heating to ensure the condition for GaN HPHT crystallization from the ferrum gallium nitride solution melt system by the temperature gradient method. The thermal state of the high pressure apparatus cell under the condition of its electroresistive heating was modeled by solving the coupled electrical and heat conductivity problem under boundary condition of the first and third kind using the finite element method. As a result of the research, the influence of the tubular heater wall thickness and the concentration of component in the axial heaters on the thermal state of the toroid 30 high pressure apparatus cell were established. See figure number 1. It was determined that the concentration of zirconium oxide and graphite, respectively of 60 and 40% by weight, is optimal for studying the solubility of GaN in ferrum. See figure number 2. Figure 3 shows the toroid 40 high pressure apparatus cell for conducting experiment on GaN crystallization. The schemes of resistant heating using composite heaters provide a temperature gradient of 14 and 8 degrees Celsius per millimeter. A temperature gradient of 13 degrees Celsius per millimeter, the aggregate chaotic growth of GaN crystals is observed. When temperature gradient reducing to values of 8 degrees Celsius per millimeter, the textured GaN polycrystals is formed. Reducing the temperature gradient while maintaining the horizontal orientation of isoframes leads to an improvement in the structural perfection of crystal. To reduce the temperature gradient to 1.5 degrees Celsius per millimeter, the high pressure apparatus resistive system was modified by using combined axial heater. See figure 3. Figure 4 shows the thermal state of high-pressure apparatus cell. In this case, it was observed the incompressible growth of petal-shaped gun single crystals up to 3 mm in size, which were combined into bushy druses. See figure 5A and B. The growth rate of such crystals, depending on the crystallographic direction, varies in the range of 40 to 150 micrometers per hour. Thank you for attention.
Thank you very much for your presentation, and let me present you. Thank you. Certificate of participation. And our next person is Yaroslav Timoshenko from Fransevich Institute for Programs of Material Science. Yaroslav, are you here? Online? Fine. No. Next, our presenter, Irina Marek from
Yes.
of Material Science. Please, you can start.
Good evening. My presentation, compositional complex ceramics based on oxide alumina. Production of ceramics based on alpha oxide alumina requires high temperature due to the high activation energy of the sintering of refractory oxides. The modifiers that cause the formation of a liquid phase during the sintering are facilitated to the reduction of temperature. Using of complex mineralizations of natural origin provides additional opportunity for achieving the required strength behaviors of ceramics based on alpha oxide alumina by varying the phase compositional as well as applying approaches of the microstructural design of compositional complex ceramics. The concept of compositional complex ceramics expands high entropy ceramics to cover medium entropy and non-equimolar composition. The aim of the study is to investigate the properties of the composite based on alpha oxide alumina containing ballast glass doped this solid solution based on dioxide zirconia. The investigation results will be used for the microstructural designing of structural materials based on alpha oxide alumina with increased fracture toughness for various applications. Thank you very much.
Thank you for your presentation. Our next presenter is Stanislav Ivanitsky from Fransevich Institute for Programs of Material Science.
One. Okay. Here we go. My presentation, the effect of rheological and crystallization properties of modified basalt melts on the drawing condition and fibers characteristics. Desit basalt are traditionally used to produce continuous fibers for composites based on modified basalt fibers composition have improved characteristics and are finding increasingly wider application in various fields. Materials. Andesite basalts, AB, which form viscose melts, were used as the main component
in the modified glass composition to accelerate the melting process and ensure the formation of homogeneous melt. Calcium metaborate, calcium B, was added to it in amounts of 5, 10, and 15 weight%. Calcium metaborate is formed during the thermal treatment of natural colemanite, which contains a combination of calcium and boron oxides. Boric anhydride, Ba, was used in amounts of 6 and 12 weight% to compare the results. The objective work was to investigate the properties of silicate systems, focusing on the impact of calcium and boron oxides on viscosity, fiber drawing processes, and fiber properties. Methods. The upper temperature limit of crystallization melts, here you'll see, was determined through a quenching process. The viscosity of the resulting glass melts was measured using a rotary viscosimeter. The modified fiber drawing conditions were investigated using a laboratory stand. The strength of the fiber was measured using a weight dynamometer. The resistance of fibers to aggressive environment was determined by their heat treatment with acid and alkalis at boiling. Results. The results of the study showed that the upper temperature limit of crystallization melts of modified gases of calcium, boron, aluminum silicate system is slightly reduced, while for boron aluminosilicate system, it remains the same as for the andesite basalt melt. It was found that the melt viscosity of all modified glasses was lower than that of the andesite basalt melt. Moreover, increasing the concentration of additives in their composition contributes to a decrease in melt viscosity, which is particularly pronounced by calcium boron aluminosilicate system with calcium metaborate. At the maximum concentration, calcium and boron additivities viscosity decreased by more than 3 times compared to andesite basalt. This leads to a significant expansion of the temperature range modified fibers production with calcium metaborate activities to 50%. It reaches 130 degrees Celsius, and with boric anhydride activities it reaches 100 degrees Celsius, while for the basalt only it is 60 degrees. Compared with this basalt fibers, the average stretch of obtained modified basalt fibers increased by up to 10%. The alkali resistance by to 10% too. The acid resistance of fibers modified with calcium metaborate increased up to 4%, while that of modified boric anhydrides, on the contrary, decreases significantly compared to this indicator for andesite basalt. Conclusion: the study result demonstrated significant effect of modification on the rheological properties and minor effect on crystallization properties of the melts. This contributed to a significant increase for temperature range modified fiber production, which is a significant positive factor in the fiber production. The average strength and alkali resistance of modified fibers increase, and slight increase in acid resistance is observed only for fibers with calcium metaborate condition. Thank you for attention.
Thank you very much for the nice presentation, and let me present you.
Thank you. Let's certificate.
And our next speaker, one of the presentation.
Mhm. Dear everyone, I would like my second presentation, basalt fibers modified with gadolinium oxide. The availability and environmental sustainability of rocks have enabled their use and production basalt fibers and related products. Continuous basalt fibers extensively used in various composite materials due to their high strength, chemical resistance, non-flammability, and eco-friendliness. The particular interest in modified fiber designed to the neutron and the gamma radiation shielding. This paper specifically focusing in andesite basalt modified with gadolinium oxide and boron oxides. Gadolinium oxide stands out among rare earth oxides due to its unicum electron-optical, magnetic, and nuclear properties. It exhibits optical transparency in the ultraviolet range, strong paramagnetic behavior, and high-temper neutron capture cross-section. The introduction of gadolinium oxide into rock smelts without adding boron compounds is challenging, as gadolinium, being a high-temperature oxide, tends to remain as non-melted agglomerates. However, adding boron compounds of the melt positively affects glass formation, leading to the production of homogeneous melts and glasses. From 5 to 10% gadolinium oxides reduce absolute viscosity values by 5-6 times. 14% gadolinium increase viscosity and prevails over the downward trend that transmitted through boron compounds. As a result, we have not only an approximation of the indicators of the initial andesite basalt, but also a significant increase in crystallization. Additionally, bondified melts 5-10% provide a sufficient temperature range, 100-110 degrees, for fiber formation, making them suitable for industrial production. Laboratory samples of basalt boron gadolinium fiber were successfully created. The modification of andesite basalt maize with gadolinium oxide in conjunction with boron compounds enhances the tensile strength of fibers by increasing the chemical resistance in alkaline environments by 7-8%. These advancements greatly contributed to the understanding of material science related to multi-component aluminum silicate melts and fibrous materials derived from rocks. Thank you for your attention.
Thank you for a nice presentation. Our next presenter is Volodymyr Polonets from one more certificate, please.
One. Good day. Among blast wounds, about 17% are bone defect, and more than a third of them are defect
defects of critical size. Their treatment requires biomaterials that stimulate bone growth and have antibacterial properties. Traditional calcium phosphate ceramics have high biocompatibility and osteoconductive properties, but do not have osteoinductive and antibacterial properties. Our previous studies have shown that doping calcium phosphate ceramics with germanium can give them these properties. However, when doping germanium metaphosphate, it was not possible to preserve the hydroxyapatite phase after annealing at germanium concentration above 1%. After annealing the bimaterial, the crystalline phase correspondent to beta-2 calcium phosphate by 100%, which significantly reduced osteoinductivity. Therefore, we used another source of germanium citrate. This allowed us to introduce 1.5 weight percent germanium without reducing the hydroxyapatite phase. In the stoichiometric sum, the structure of the hub was completely preserved, and in the non-stoichiometric one, a three-phase biocompatible ceramics with good biological properties was formed. In vitro and in vivo tests confirmed the high efficiency of the material. Sample with germanium citrate inhibit the growth of bacteria. And when implanted into a bone defect of critical size in a rabbit, complete restoration of bone tissue was observed. Has doping with germanium citrate made it possible to create a calcium phosphate ceramics that combines osteoinductive, antibacterial, and antiviral properties. This material has great potential for use in bone tissue engineering. Thank you for your attention.
Thank you very much for your nice presentation, and it's your
Thank you.
certificate. Our next presenter, Larissa Waits from Francevic Institute for Problems of Material Science.
Один-один.
Good afternoon, everyone. Today I'd like to talk about comparative studies of phase and structural changes in calcium phosphate ceramics, CPC, after exposure to blood plasma and acetic acetate buffer, AAB. A direct study of behavior of calcium phosphate ceramics after implantation into bone tissue, especially with a high level statistical reliability, is impossible. However, understanding of this behavior is critically important for optimizing the properties of CPC intended for bone tissue restoration in specific clinical cases. As an initial experimental step, the effect of human blood plasma on monophasic H and biphasic HT was investigated. And acetic acetate buffer with pH of 7.4, mimicking blood plasma pH and free of calcium phosphate, was chosen as a physiological simulated fluid. The samples were incubated at 37 degrees Celsius for 24 hours. Subsequent material solubility analysis revealed a decrease in the concentration of calcium ions after 24 hours of immersion in human plasma. Blood plasma is a supersaturated solution of calcium phosphate, leading to precipitation of calcium phosphate onto the material surface. X-ray diffraction analysis confirmed the absence of new crystalline phases. But for the stoichiometric hub, the reduction of amorphous halo after AB exposure may indicate a decrease in the amorphous component of the material. The rightward shift of the diffraction peaks in biphasic CPC diffractogram indicates a reduction of the crystalline lattice parameters under the influence of acetate buffer. Microphotographs of the CPC show that after blood plasma treatment, an organic film forms on the stoichiometric hub composed of absorbed proteins and other plasma components. Moreover, the solubility results indicate the precipitation of calcium compounds from the plasma onto the CPC surface, which combined with the organic deposits leads to the filling of the interparticle gaps in hub. The obtained data can be used for further experiment planning and for determining the direction of material property modification aimed to enhancing its activity. Thank you for attention.
Thank you. Nice presentation. And our next presenter is from Conservation Institute for Global Development.
Я просто... Еще больше.
Good afternoon, dear colleagues. The topic of our investigation study of the semiconductivity of A2B2O7 compounds as potential materials for thermal barrel coatings. The rare earth complex oxides are of great interest for material science due to their many technological applications. The rare earth D-titanates, D-gaffnates have been considered as promising candidates for next-generation gas turbines thermal barrier coatings materials because of better phase stability and reducing thermal conductivity. In contrast with the currently used yttria, partially stabilized zirconia. Some members of series are also very important for the tissue engineering, aerospace, and power generation industries. At the same time, many of their properties, especially thermophysical ones, have not yet been studied. The present work focuses on investigation of the thermal conductivity of praseodymium, neodymium, europium, and ytterbium complex oxide. The sample was sintered and 1,480 hours, and pellets were analyzed and 1,400 for 2 hours and 4 hours. The obtained samples were characterized by X-ray diffraction. The measurements of thermal conductivity of sintered pellets were carried out for the first time in interval 313, 673 in the monotonous heating mode using dynamic calorimetry method. Conclusions. Figure 1 demonstrates the specific heat temperature dependencies of rare earth complex oxide were calculated according to the Neyman-Cope law for the first time, and then that were used for computation of thermal conductivity. The thermal conductivity of investigated rare earth complex oxide does not show the classical dependence. In general, rare earth metals dititanate display low K values, then rare earth metals digaffinates analogs in all measuring temperature interval. It was found that the thermal conductivity of A2B2O7 partially depends on the time of heat treatment of material. The longer the annealing time, the lower its porosity, and accordingly, the higher the K values. This can be seen in the figure 2. For praseodymium-2, hafnium-2O7. Among testing samples, the perifluor type europium demonstrates the lowest thermal conductivity at 600 Kelvin. This result is similar to those found in literature for isostructural digaffnate. Rare earth titanates must be an attractive component for creating a new TBC material. Thank you very much.
Thank you very much for your presentation. And our next presenter, Alexander Parfyomov from Kenya. For programs of material science.
Plus 1, 2. Okay. Hi everyone. Today I want to present our study of temperature-dependent mechanical properties of silicon carbide polytypes with DFT-derived machine learning potential. So the problem is it's very important to characterize temperature-dependent properties of of materials with industrial significance. And we have very powerful tools like density functional theory to get those properties, but the problem is they are very limited to in terms of size of the systems, because this approach is computationally very expensive. And to deal with that, we can use machine learning potential in interatomic potentials. And that was exactly what we use in our study to get the mechanical properties of most two significant polytypes of silicon carbide, that's cubic and hexagonal one. And to get this, to obtain this interatomic potential, we first used the data from open sources such as Nomad repository of DFT calculations, and as it turned out, we didn't get good results for some of the known mechanical properties with this potential, but eventually, we made our own DFT calculations. That's around 5,000 configurations at different temperatures, and on that data we trained more robust interatomic potential. And as we can see in plots, the results of convergence were faster and better. With this potential, we were able to make simulations on the scale of not like tens or maybe even less of like number of atoms, but actually on a scale from 2 to 6,000 atoms. And with that, we were able to get elastic constants, which we present as a plots versus temperature at the top center plots, and also simulations for coefficient of thermal expansion were obtained for both of those polytypes, and they matched the results of the experiment also very well. Also, we can see the result, like the effects of the system size on Symposium. Oops. Yeah, this one plot. This reddish line is depicts a more smaller system with only a few hundred atoms, and it's getting more destabilized with the temperature. Then we use simulations to obtain some uniaxial Young's models for both polytypes, and we obtained a quite interesting result for direction of C-axis, where hexagonal polytype degrades faster. It's like 2 times faster softening rate compared to qubit 1. So, but other than that, averaging modulus for Young's and bulk modulus aren't like consistent with other results that presented in the literature. That's probably it from my side. Thank you very much.
Thank you for your presentation. This your
Thanks.
participation. I will next present Dmitro from Kyiv Academic University.
Yes, hello everyone. Today I want to present my study on using GPR to select the heating rate in SPS sintering of titanium nitride. Precise control of the densification rate during spark plasma sintering is critical for tailoring the microstructure of advanced ceramic materials. The study aims to apply machine learning technique to optimize heating rate profiles for controlled densification of titanium nitride. Regardless, a regression model based on Gaussian processes was developed and trained using experimental SPS data for titanium nitride. Multiple kernels were probed, including radial basis functional, Matern, rational quadratic, and so on. Best results were achieved with rational quadratic kernel. Data processing included normalization, signal smoothing with a 10-second sliding window, thermal expansion correction. Based on final density and piston travel data, a density was calculated for each point in the dataset. The proposed GPR model successfully forecasts the densification behavior and enables a virtual sintering experiment under constant and variable heating conditions. The model predicts the piston displacement based on sintering time, prior displacement history, and both current and next steps temperatures. The model generates heating profiles that yield displacement curves closely matching experimental results. Using the model, it was possible to generate heating profiles that are close to the optimal densification profiles as described in literature. Average difference between predicted values and theoretical values was 8%. This confirmed the feasibility of using data-driven models to select optimal heating schedules. The approach can be extended to optimize additional SPS parameters such as pressure. Further SPS experiments are being developed to validate the predicted regimes. That's it. Thanks for attention.
Раз, два, три. 1, 2, 3. 1. 1, 2, 3. Okay. This.
One of the fundamental challenges of structural materials regard one of the fundamental challenges of structural materials,
Excuse me.
regardless of their chemical or phase composition, is their tendency to stress concentration. Localized stresses near defects and cracks significantly exceed nominal values in undamaged regions. As a result, only a small volume of a load-bearing structural element, typically near a crack, actively resists fracture and ultimately governs the strength, fracture energy, and weight efficiency of the material. In contrast, biological structural materials exhibit a minimal tendency to stress concentration and brittleness. These materials have been refined and tested over billions of years, a period unmatched by any man-made material. Therefore, the morphology and mechanics of biological structural materials are clearly superior for structural materials in general. Biological structural materials are heterogeneous and possess a multi-level hierarchical structure. Each level consists of parallel, overlapping scaly or fibrillar load-bearing elements aligned with the direction of maximum normal stress. These elements primarily carry normal stresses along their longest axis. Interfaces between them possess low shear resistance and therefore prevent the stress concentration. Thus, the existence of a single shear direction on extended interfaces, which is oriented along trajectories of maximum operational normal stresses, can be considered the main feature of the best structural material.
This is example of biological structural materials, silk, nacre, bead wings, and artificial view-inspired structural materials on glass fiber, carbon fiber, and TTL layered structures. Thank you very much.
Thank you very much for the presentation and this video certificate of participation.
Ох, я украл.
Dear colleagues, thank you very much again. And we are waiting for you tomorrow. Tomorrow we have simultaneously two sessions. It's metals and alloys and functional optic materials. Offline locations on functional optical materials will be worked in Kharkiv and in Kyiv. And in Kyiv, we also will have offline locations for metals and alloys symposium tomorrow. So we are inviting you to join us offline, or maybe for some participants, international participants online. See you tomorrow.
See you.